SharePoint?
Yeah, so there people are entering now.
Yeah.
Oh, wow, I see. You guys had a waiting room. I see.
Yeah.
You are online.
Okay, so we just wait. Okay, so it's 9. Good morning / good afternoon, good night, everybody. And I just give the floor to Anna Sampera, who will be chairing the session this morning. Anna, please.
Hello, good morning, everybody, or good afternoon, or good evening for some of them, which is quite late. So it's a pleasure to have this morning, this new session in this time. Crystals. So our first speaker this morning is Norman Yao from the University of Berkeley, which is going to talk about periodically driven classical time crystals. Norman, please go ahead, and thank you.
Wonderful. Yeah, I'd like to start by echoing the other speakers and thanking the organizers for putting together this super fun and interesting program. So one thing you might have noticed is that my talk title has changed a little bit quite a bit since it was posted online. And the reason for that is at the moment it's midnight in Berkeley, or just past midnight in California. But I've spent quite a bit of today catching up on talks. I haven't finished watching all of them, I have to admit, but I've seen quite a few talks. And I have a sneaky suspicion that this particular topic of classical time crystals maybe will generate more discussions. So I decided to pivot towards it. There are two parts in the talk, broadly speaking. The first part is based on some work that's already published with Chetan Nayak, Leon Balance, and Mike Zaletel. And the second part is some it's been ongoing for a long time, so we hope to finish it soon, work together with my student Francisco Machado, my postdoc Trintao Zhuang, and Mike Zaletel. So I think we've been hearing lots of talks where the setting's been sort of made clear, but just to make sure that everyone's on the same page, I wanted to sort of go through a little bit of my perspective and just give a very, very sharp kind of specificity on what the question I'm going to ask is. Mainly the talk will be about classical systems, but I wanted to start with the quantum setting just to make sure we're all on the same page. And the setting specifically is periodically driven systems, where we ask the question whether or not there can exist a subharmonic response. So here, this is just some operator, some position, some spin, for example, which is, we're looking at it stroboscopically as a function of the driving period. We're specifically assuming that it's period doubled, so it'd be a nu equals 1/2 type subharmonic response. And the question always to keep in mind for this talk is basically, what is tau? So in the sense of long-range order, if we say that there's kind of temporal long-range order and that the subharmonic response has this analogy to what we'd like to think about with respect to kind of symmetry breaking and long-range order, we're asking whether or not the autocorrelation time for this particular type of subharmonic response can be infinite or not. And the challenge in either the classical or quantum situation for a many-body, strongly interacting, periodically driven system that kind of fights against this infinite autocorrelation time, of course, is that one expects at late times that the system kind of slowly will absorb energy via interactions with the drive, and this goes typically these days under the moniker of flow K heating. There are a number of strategies. I'm not going to be exhaustive. There's been lots of talks, so I've learned new stuff as well. But one strategy in the quantum setting goes under the name of many-body localization. In MBL systems, the idea is super simple, that one uses disorder to induce localization would prevent the system from heating up. And it's sort of believed that in this setting of a time crystal, so a many-body localized time crystal, that indeed the autocorrelation time goes to infinity. Of course, there are other restrictions. This ties the stability of the time crystal to the existence of many-body localization, which at the moment we think is true in 1D. It's not super clear whether it's true in dimensions greater than 1. There's another strategy, which goes under the name of pre-thermalization. And here, the basic idea is also very simple, where one uses control of the driving frequency to make the absorption this flow K heating rate extremely slowly. So in this case, one doesn't have a kind of a true, maybe in quotation marks, time crystal, in the sense that the autocorrelation time is exponential in the drive frequency. So it's, it's finite in the thermodynamic limit. But I would say kind of for all intensive purposes from an experimental perspective, it's impossible to tell the difference between a pre-thermal and many-body localized time crystal just by looking at this tau. There are also restrictions for pre-thermal time crystals. One of the most well-known ones, of course, is that it requires one to have finite temperature symmetry breaking. And at least for short-range interacting systems or local interactions, this means that the physics of this pre-thermal time crystal is restricted to dimensions greater than 1. Actually, so this was going to be the majority of my talk that I had planned in the abstract, and these is the theory in the experimental paper I was planning on talking about before deciding to pivot earlier this evening. Of course, the last and maybe most obvious strategy at some level is to use dissipation. In the context specifically of quantum systems, this means a Hamiltonian plus some sort of Limbladian dynamics to allow for explicit cooling. But if one really thinks about this as coupling the quantum system to a bath, then there's always the question of what happens, what's the interplay between the noise and the subharmonic order that one expects in the time crystal. So the talk today is going to focus on, all it's going to do is we're going to change the word quantum to classical. And these three particular strategies, we're going to ask a question about one of them, but we can emphasize that, at least as far as we know, many-body localization kind of doesn't have a strict classical analogy. Pre-thermalization actually does have a kind of very nice and sort of precise strict classical analogy, and there's some really, really pretty papers from Mori looking at classical pre-thermalization. But the specific context that I'm going to focus on today is, again, dissipative classical systems. And I'm pretty specific by that. I mean that really we're going to think about a Hamiltonian system plus Langevin dynamics, where in this case, you're really thinking about it again as finite temperature. So you do have dissipation in the Langevin dynamics, but that via fluctuation dissipation comes with noise. And the question we'd like to ask is, can one get a time crystal with an infinite autocorrelation time in the setting of a classical system governed by Hamiltonian plus Langevin dynamics? Let me again emphasize, these three strategies exist. They're not the only strategies. I mean, Angelo's talk was super interesting on alternate things that one could think about in classical systems as well. Good. So just as a little roadmap to be super specific, there's two parts to the talk. The first part is just going to be kind of trying the dumbest thing you could imagine. So let's take a look at a generic, nonlinear, classical 1D system undergoing Hamiltonian and Langevin dynamics and see what one finds. And part two is we're going to be a little bit more clever about the Hamiltonian, and we're going to use an analogy to cellular automata. So what's the setting for part one? It is, I think, in some sense, the most natural and simple system one can consider. So we consider a 1D array of parametrically periodically driven coupled nonlinear oscillators, where there's nearest neighbor coupling between the oscillators I and j. There's a drive at frequency omega d with amplitude delta, and the nonlinearity in the oscillator comes from the fact that it's a cos qi, not just a q squared. That's the Hamiltonian, but our goal is to understand, if period doubling exists, the stability of period doubling relative to this periodic drive under Langevin dynamics. And in Langevin dynamics, I'm sure everyone's super familiar, but let me just be specific again. There are two terms in the Langevin dynamics in the sort of Langevin force. One of them is given by, dissipation coming from a friction-like term. So that strength is given by eta, and of course it couples to q dot, the position, the derivative of position. And the second is kind of a stochastic noise, C of t, which you can really think about as being related to dissipation via fluctuation dissipation with a coefficient that's precisely the temperature of the system. So before even getting into the 1D system, let me just remind us what the lore is. There is a long, long history on this problem. So if one imagines, for example, a single parametrically driven nonlinear oscillator or a single parametrically driven pendulum, this is the kind of zero-dimensional starting point. At t equals 0, there exists very well-known subharmonic responses. So these are Arnold tongues, not exactly the same thing, but a nice picture here. And the statement is that when one has a forced pendulum at t equals 0, one can get oscillations at a fraction of the driving frequency. Here are some super simple numerics where the drive is in green and the pendulum response, for example, is in blue, and it sort of doubles the period of the drive. If you just look at the position of the pendulum, then it goes from up to down, up to down, up to down as a function of time. And in this stroboscopic view, that kind of looks like this, this stripe pattern. But I'd like us to always, at least for the remainder of this talk, take sort of the stroboscopic even view, where one only looks for the response at every other period. So when one sees sort of solid splotches of blue or red, that's kind of consistent with period doubling. And when one sees, for example, something that looks more white, that actually is going to be the absence of period doubling. Just to be clear how we're getting to this shade over here, if you start in the period doubled phase for kind of a single, the parametrically driven pendulum for a single pendulum, and at t equals 0, there exist very, very sharp boundaries between regimes, for example, of period doubling and regimes where there's no subharmonic response. In our simulations, the main tuning parameter for us is super simple. It's the ratio of the damping, which was eta, to the driving amplitude of the periodic drive, which was delta. And we take that ratio to be lambda. And if one increases lambda from the previous plot where we once saw period doubling, then one naturally can see that at large lambda, the period is no longer locked to any period of the drive. And we can see, for example, that from the stroboscopic viewpoint, that there is no longer kind of this nice oscillation for the pendulum. So you've sort of melted away any of the harmonic responses from this. Again, all super well-known stories at t equals 0. The transition as a function of lambda at t equals 0 between period doubling and this non-period double behavior is sharp. But as you might expect, at any finite temperature, these sharp boundaries between, for example, period doubled and non-period doubled behavior have to blur into a crossover. This sort of thermal noise leads to phase slips, and that blurs the sort of phase boundaries. And this agrees with kind of very, very standard stat-mech lore that in a 0D system, one can't get a sharp phase transition at finite temperature, right, in a 0D system. Just to be super clear, the diagnostic of period doubling that we're going to use is something that's used in the literature very often called the velocity parameter. The velocity parameter is just the fact that, you know, the derivative of the position knows about the resonant response of the system. And if that resonant response of the system is at omega d over 2, so when omega q equals omega d over 2, v is equal to 0, and that means we're in the period doubled phase. And if v is finite, that means we're no longer in the period doubled phase. And doing numerics on a single pendulum using a simple Langevin stepper and varying lambda, you basically see that indeed, as you change lambda, v goes from kind of period double to non-period double behavior, but it's clearly happening via crossover. And this is consistent with the fact that there, again, is no sharp phase transition allowed for a single pendulum at finite temperature. So we can ask the question, what happens if we now go to the system of interest where we actually now think about a 1D system of coupled pendula? Again, still very classical, very simple physics. At t equals 0, it turns out the answer is still known, and one has kind of similar behavior to that of the single pendulum case. I feel like in the literature, it's more often called subharmonic entrainment in this sort of one-dimensional coupled case. But again, at 0 temperature, one can get, for example, a subharmonic period doubled response or period tripled response. And there is a sharp phase transition between the kind of period doubled phases and the non-period doubled phases. At finite temperature, it looks like if you do naive simulations, that the behavior is kind of similar to the single pendulum case. So here now we're looking at, I don't know, a couple thousand pendula where the x-axis is pendulum sort of 1, 2 indices of the pendulum index, and the y-axis is time moving downwards. And again, At low values of lambda, our tuning parameter, at low values of the friction divided by the drive amplitude, one sees period doubled behavior. At high values of lambda, one sees not period doubled behavior, the melting of this period doubled behavior. And it looks like at intermediate values, you get domain walls, but maybe the crossover is kind of smooth. So the physics question that one can immediately ask is there anything sharp for a 1D system of coupled nonlinear pendula at finite temperature? Or like the 0D case, is it just a crossover? Again, in equilibrium, a sharp phase transition is strictly forbidden in one dimension. But we're not in equilibrium, so maybe the situation's a little bit more rich, and that's what I think I'll hope to convince you of. So it turns out one can again do the exact sort of same numerics. At high temperatures, we're looking at the velocity order parameter average over the whole many-body system as a function of this tuning parameter lambda. Again, at small lambda, you see something that's consistent with period doubling. And at high lambda, it looks like a pretty smooth crossover to the melting of the non-period doubled phase. But something kind of interesting happens at low temperature. In particular, when one goes to low temperature, one finds that this velocity order parameter, when one changes lambda, it looks like it sort of jumps on the way up and has a hysteresis loop on the way down. And as you slow down the rate at which you change lambda, as you increase the number of steps with which you sort of, basically the number of steps of the Langevin stepper, you find that this hysteresis loop gets smaller and smaller and smaller, much like you'd kind of expect for a first order phase transition. And a sufficiently sort of slow variation of lambda, you basically find what looks at like a pretty sharp phase boundary emerging at low temperature. So at any finite temperature in 0D, it's always a crossover. In 1D, you might expect from equilibrium stat mech intuition that it's also always a crossover, but it seems like we see a distinction between the physics at high temperature and low temperature. So the question we can ask very simply is there indeed kind of a sharp phase boundary emerging at low temperatures? If we now look at a different diagnostic, maybe the sort of nicest diagnostic, I would say, is to set up a very, very simple domain wall and watch the subsequent dynamics. So what we do here is we literally set up an initial condition, which is kind of trivial, no period doubling on one side and period doubling on the other side. And then we set the parameter lambda to be somewhere in the phase diagram. And we ask what the subsequent dynamics look like. And you can see when you're in the non-period doubled phase that eventually the sort of, trivial phase sort of eats the time crystal. And you, of course, sort of, ultimately get to a situation where the full system it lacks period doubling. But if one now literally zooms in to a very, very small splotch, lambda is varying from 0.195 to about 0.215, so very, very close to the phase transition. You see that if lambda is just a little bit smaller than what we would say is the critical point, that when you start with these two regimes, in fact, the time crystal wins. When you start just a little bit above, then you see that the trivial phase wins. And if you're right at the phase transition for many, many millions of cycles of the Langevin evolution, you basically see competition between a period doubled, between the sort of domain wall for the period doubled and the non-period doubled phase. So if you zoom in just a little bit further as a function of time, it really does look like there is a sharp phase boundary emerging as a function of lambda. And you can identify sort of this phase transition between period doubled and non-period doubled physics at some critical point in lambda. So this kind of ends sort of, what I would think is a sort of a sort of nice, simple foray into the story of coupled nonlinear oscillators, where we think that the phase diagram computed numerically for this type of a system is that at high temperatures, it's kind of like water, in the PT phase diagram of water in some sense. At high temperatures, there is no phase transition. You cannot walk as a function of lambda across a phase transition between the time crystal and the non-time crystal phase, or the period doubled and the non-period doubled phase. But at sufficiently low temperature, and as you increase lambda, you can in fact walk through a first order phase transition between the period doubled phase and the non-period doubled phase. And we believe that there's a line of kind of first order phase transitions that basically ends at a critical point. So you'll see actually that the title of this slide at the moment still says time crystal-ish. And I should really emphasize that this ish refers to an answer to the question that I posed in the very first slide, which is the autocorrelation function of the time crystal infinite or not? Or is the time crystal only stable for maybe a long but sort of finite time? So there's a phase transition here, not because the lifetime of the time crystal goes from infinity to some finite number, but because it goes from something that has exponential dependence to something, again, that's order 1. So it's this, analytic dependence of tau on temperature that kind of is undergoing this first order phase transition across the transition. And again, let me emphasize, what this means is that we don't really have an infinite autocorrelation time crystal in the sense that there's no kind of true long-range order. This tau, this autocorrelation time, is indeed activated. So it is exponentially large in temperature with some delta. You can think about it as some barrier that kind of depends on this lambda, but again, it doesn't have this infinite autocorrelation time. So I would say that for part 1, the take-home message is pretty simple. Although the model we've been looking at has, I think, a very, very interesting phase diagram and an interesting interaction-driven, sort of intrinsically non-equilibrium phase transition. Remember, in equilibrium, you're not allowed to have such a phase transition. You don't have an infinite autocorrelation time, so you don't really get a time crystal. But in some sense, we started out with a Hamiltonian that was the simplest possible Hamiltonian you could imagine, coupled nonlinear oscillators. So we can ask a question, if we're allowed to vary the Hamiltonian from part 1, can we be clever and actually realize a time crystal in this classical Hamiltonian plus Langevin situation that has an infinite autocorrelation time? So the setting is still Hamiltonian plus Langevin, but now we're going to get a little bit more clever with how we design the Hamiltonian. And in particular, that cleverness is going to borrow some inspiration from the land of cellular automata. So I think everyone's familiar with pictures of cellular automata, but I just want to give a very, very intuitive connection between why it's kind of natural to think about the connection to cellular automata. And the connection's super simple. We generally think of Langevin dynamics, or kind of, the Fokker-Planck equation before that, as some example of a continuous time Markov process, where you have some probability distribution for Q and P, position and momenta, and the time dynamics of that are given by the Langevin dynamics. The analogous construct for cellular automata is kind of the discrete time version of a very similar Markov process, where again, you have some probability distribution of sigmas, and they undergo some transition matrix M to a new probability distribution at some time t+1 in a discrete fashion. Of course, there's a small difference, something I've been emphasizing throughout the talk, is that one important thing to consider from Langevin dynamics is that you naturally have errors, that you should always think about there naturally being errors from the fluctuations intrinsic to finite temperature noise. So really, the slightly more proper analogy is really to think about the connection between Langevin dynamics and cellular automata not being just a cellular automata, but really being what we call a PCA, or what the literature calls a PCA, which is a probabilistic cellular automata. So the probabilistic cellular automata is the same thing as what we previously had, except now the transition rule, the transition matrix here, is your old cellular automata transition matrix plus, for example, some random errors. And this I think of as kind of the same, similar as analogy to the random errors that one naturally gets from Langevin, from finite temperature noise in the context of Langevin evolution. So the question at this stage, before using this intuition from a PCA to construct a Hamiltonian, I want to first ask a question, which is whether or not a PCA itself can support a time crystal. And it turns out there's also some really nice related work from Pizzi, Neunenkamp, and Knoll in the context of long-range PCAs Here, we're specifically thinking about locally interacting, so nearest neighbor interacting probabilistic cellular automata. But the key point is that any time crystal requires ergodicity breaking. You have to break ergodicity because you have to remember the subharmonic orbit that you stay in. In the MBL case, you break it because MBL breaks it. In the prethermal case, you break it because you're prethermal and you know about symmetry breaking in one of the sectors. The remarkable thing is that PCAs, so probabilistic cellular automatas, are super well known to support ergodicity without fine-tuning. The classical example of that is something called the 2 model, or the northeast corner rule. It says that this blue cellular automata cell, it's a 2D cellular automata. It says that this blue cellular automata cell, majority votes based on its north and east neighbors to figure out what its next transition rule is. And the thing about this cellular automata is that there exist 2 stable distributions without the need for symmetry. So you might say 2D, 2 distributions, this seems like a ferromagnet. Like if I think about like classical stat mech, I can have a ferromagnet or Ising symmetry breaking at finite temperatures in 2D. But here it's much, much stronger for the PCA construction because you don't need the symmetry. You can have biased noise, for example, you don't need the symmetry, but there are still 2 stable distributions. In some sense, the all up and the all down state, but you don't need to have that Ising symmetry to have this type of symmetry breaking, to have these 2 stable distributions. Just a couple more slides, I'm almost done. So just to give a sense, just a super quick video of what happens here. It's a pretty boring, it's not that interesting video. It's a 2D grid of cellular automata, and the 2 possible states of the cellular automata are yellow and purple. And what I mean by stable distributions is just if I make a little chunk of purple and let the cellular automata evolve, then it naturally sort of, goes to the stable distribution. It eats that purple away, sort of error corrects. In the same way that if you had all down as the ferromagnetic state, a finite temperature fluctuation would never take you to all up. So in the next setting, in this particular setting, it means that we can immediately, basically, and somewhat trivially define a PCA that's also time crystal by simply taking the kind of flip version of the 2 model, where you apply the same rule, the same PCA rule, but followed by a global spin flip. So in this situation, the dynamics look like a global spin flip. So there's still a region, it still gets eaten away as a function of time, but now in principle, just kind of trivially from proofs of the properties of this northeast corner rule, one automatically gets a PCA time crystal with an infinite autocorrelation time, which is robust to noise and local perturbations. So the noisy version of the simulation also eats away at this, and you have, in principle, an infinite autocorrelation time in this probabilistic cellular automata model in 2D. It turns out, I think that's already pretty cool, but it turns out there's a kind of a very, very natural.
Sorry, you have 2 minutes more.
2 minutes, yeah, okay, wait, this is last slide. So it turns out that there's a supernatural way to translate PCAs to Hamiltonian simulations. And in particular, one can translate the PCA, just kind of a Hamiltonian plus Langevin simulation. There's a sketch of the simulation over here, but what I'm showing over here is really numerics that look at a cellular automata with some error, which means a probabilistic cellular automata. And you can see that as a function of some pinning potential, which is a property of the Hamiltonian and the Langevin numerics, you indeed see the pinning of the magnetization, which is consistent with the time crystal. So this, I think is sort of a nice numerical demonstration that indeed we can simulate more or less an arbitrary probabilistic cellular automata with a Hamiltonian plus Langevin formulation. Let me just end here. I won't go into any further slides, but let me just say that a very interesting question is whether or not the same thing holds in 1D. Can you have a Hamiltonian plus Langevin situation in 1D or a PCA in 1D that also is a time crystal in the same way? We believe the answer is yes. It's related to some beautiful work from Peter Gotch, but yeah, maybe I won't go into too much detail. But we believe that the answer for 1D, the same question for 1D can also be answered in the affirmative. With that, let me just stop here and thank you for your attention.
Okay, thank you. Thank you very much. There is a couple of questions, sorry, because we are a little bit sharp on time. So Jamir, do you want to start with your question?
Yes, thank you so much, Noam, for the talk. Hi. So for the first part, do you have any type of Landau-Ginzburg picture? Normally, these first-order phase transitions occurs because you jump from a local minimum to a global minimum. And one way in which you could get sensitivity is a finite size scaling analysis, because typically the time that you need to tunnel and to get the jump will start to increase exponentially with the height of the barrier, that is the system size. I'm saying that while you think about it, because there was this nice work by Stefano Ruffo on the Kuramoto model with noise and damping. They have long-range interactions, okay? So it's nothing to do with what you're talking about. But they developed that at the end of their paper. It's a PhysRev E. I don't know if you are aware of it.
Yeah, I wasn't aware of that specific paper, but the strategy that you said is super logical. And actually, it turns out you can kind of map the problem that we were looking at in the first part to sort of a DC-driven version of a friction question of the Frankel-Kontarova model. So we tried to do this kind of a Landau-Ginzburg analysis in this, a related analysis in the context of this DC-driven Frankel-Kontarova model, but we weren't really able to make too much progress because it's kind of an intrinsically non-equilibrium phase transition. So sort of, it doesn't, at least for us, it sort of, was a little bit more that we kind of needed to use sort of non-equilibrium tools to even see the transition in a 1D system. I think in the all-to-all coupled system, you have this mean field limit, so it's much more well controlled. But in 1D, because the transition's intrinsically non-equilibrium, we couldn't quite use the same techniques as far as I understood.
Thank you.
Let's move another short. Yeah. Okay. Christoph, maybe you have your question. I'm sorry because there is a lot of questions, but we will not have time for all of them.
Sorry.
So go ahead, please.
Okay. In the formation of quantum time crystals, we know that the central phenomenon is the spontaneous breaking of the time translational symmetry. Of course, we know that in the classical mechanics, consequences of translation or any symmetry is very different. Because, for example, there is not a problem to have a single particle which reveals period doubling. So, do you agree that this is, of course, this many-body synchronization in a classical system is very, very interesting and out of question. But do you agree that this is hard to say that in classical system we have a spontaneous breaking of the symmetry?
I literally can't agree more. I mean, I think that's exactly right. So maybe let me just sharpen that a tiny bit or give my own perspective on that. In the quantum case, we're used to, really having a periodic system and thinking about this time translation, like, discrete, if, the Floquet system, has a period that kind of varies, you sort of no longer have the physics. The physics isn't stable to that. But for example, for this PCA here, or for the, the model that we were starting out with, there's no notion, if I had a little bit of a variation in the period as a function of time, that wouldn't matter at all. So I think it's really, that's right. In the classical setting, I think it's not really the kind of breaking of time translation symmetry, but it's really related, I think more globally to this question of whether or not you have ergodicity breaking or not. But I totally agree, Christoph.
Okay, let's take another couple of questions. It's very interesting. So Izar, please, can you go ahead? You have to unmute.
Yes, my question is about the symmetry. So you say that there is a no symmetry. So Hamiltonian is basically dependent on symmetry. So how could you say that without it doesn't depend on symmetry?
I have to admit, I didn't hear it super well, but I can try to answer what I think I heard, which was that, the question was kind of, if there's no symmetries in the Hamilton, like, how do you think about time crystals if you don't have a symmetry? I think the point is just, in some sense, there's no sense in which the time evolution has to be truly periodic, or like, imagine that you have a period and, you're more or less, almost always, the period is time t, but, sometimes the period of the evolution is t plus delta t. Sometimes it's t minus delta t. So strictly, there's no time translation symmetry, and you can't break that symmetry. But I think in the classical setting, at least for either the PCA scenario or the Langevin dynamics of the nonlinear oscillators, that's not required. I think all you need is basically ergodicity breaking. So I think that's sort of what I mean.
Okay, can I ask a quick question, a simple question?
Yeah.
So I have a question related to your first part. I'm thinking that have you kind of simplified the model to explain your results? For example, maybe each nonlinear oscillator has a bistability, has some kind of bistable states. Then you can represent each a non-linear oscillator spin up and spin down. Then the time crystal state maybe correspond to some kind of ferromagnetic or antiferromagnetic kind of state. Do you have such kind of simplified model?
That's exactly right. I mean, so literally, I mean, the fact that you have this bistability, so I think maybe it's like figure 2 in our paper, the fact that you have this bistability is the origin of this behavior. But I think, you know, the question isn't that, you know, so certainly this bistability for a single parametrically driven oscillator underlies the time crystal, but kind of what we were more interested in, or at least what was a little bit more exciting to me, so that definitely is the underlying physics, you know, that bistability. But the question was whether or not when you couple a chain of oscillators and you go to a finite temperature, can you have a phase transition between this sort of bistable kind of, you know, time crystal and the non-time crystal phase? You know, because in equilibrium, you would expect the answer is no. And I think in this case, you basically see that the answer is yes. And it's because you have a non-equilibrium system, so you're not really governed by the same Statnek laws.
Okay, thank you.
Thank you very much. Sorry, because there are other questions, but we don't have time. So please, I ask you to write it into the chat to Norman, and we are going to enter Vedika Kemani, please, for this second talk. So thank you, Norman, and it's my pleasure to introduce now Vedika Kemani, who is going to talk, if she has not changed the title, which maybe she has, many body physics in the NISC area or times. So.
Okay, can you see my slide?
Yes, you have to make it
yeah, we
the format of presentation.
Oh, I see. You only see part
because
of it.
It's
okay.
now
Just 1 second. Yeah, just 1 sec.
It's a time crystal. It's double, you know.
Yeah. Okay. Okay. Let's go there. Okay. How about now?
Now.
Is that good? Okay. Great. Yeah. I didn't fully change my title. I only dropped a part of it. So to make it less of a mouthful, but the second clause is the same. Okay. Yeah, thanks very much for inviting me. Today I'll be telling you about a recent proposal that we put out to realize a time crystal on Google's digital quantum simulator. This is their so-called Sycamore chip that many of you may have heard about last year in the context of quantum computational supremacy or advantage. But before diving in, I really want to thank the organizers for putting together this really nice workshop. While this beautiful physics of macroscopic oscillations and subharmonic responses has a long and storied history, it's been very interesting to me to see the rich variety of new and different physical settings in which this phenomena can show up. And indeed, much of our modern world would be nowhere without the physics of macroscopic clocks. I've really enjoyed hearing about how many interesting questions still remain to be explored in understanding these really fundamental phenomena. So, now my background is in condensed matter theory. So when I say time crystals, I specifically mean that I'm referring to many body time crystals, right? And in this workshop, this context, this question of how strict we should be in defining time crystals and which phenomena would correspondingly be included has come up a few times during various talks. So what I want to do is I want to start by clearly defining what a time crystal means to a many body physicist, right? And then I'll give you a brief summary of the experimental situation on time crystals and motivate why we even need another time crystal experiment, right? Because you might think that, okay, we already have all of these different experiments. You know, we had the different experiments from now 3 years ago. So why is this proposal on Sycamore's chip, you know, timely or relevant, right? And then I'll finally get into the details of the proposal itself and describe that, okay? And I want to just advertise that, you know, late in 2019, we put together a very detailed review where we discuss a lot of these questions, especially, you know, how we should think about many body time crystals, what are various like adjacent phenomena like that are similar in spirit to time crystals, the experimental situation. So I won't have time to go into this in much detail in the talk, but I urge you to look at this review if you're interested. Okay, so let me start with this question of what many body quantum time crystals are, right? And the very first thing, as the name might suggest, is that, you know, when I'm talking about a many body time crystal, I really have in mind a system with many coupled degrees of freedom. So this is not a problem that you can describe in terms of one mode or two coupled modes, not just one or two differential equations, but really many coupled degrees of freedom, all of which are strongly interacting with each other and all of which constitute the system, right? So in fact, you know, when I first arrived at Harvard in 2016 as a postdoc, Bert Halperin asked me a question, which was that, you know, we have macroscopic oscillations all the time. Indeed, imagine that you had a macroscopic pendulum. You know, this is an actual pendulum clock, a pendulum bob. This has 10 to the 23 atoms. You would say it's many body for all practical purposes. And now imagine sticking this pendulum in your favorite vacuum bell jar and making it frictionless and all of that stuff. And then you would say that this pendulum actually should oscillate forever, right? So should we call that a many body time crystal? And this was, of course, you know, a key question, and it deserves a careful answer. And the point here is, really, should we think of this macroscopic many-body pendulum, which is made up of some real material, should we think of it as a single mode, right, the center of mass mode? Should we describe it as one mode, in which case, if we stick it in this frictionless bell jar, indeed, it will oscillate forever? Or should we think of this pendulum as actually having all of its numerous internal modes, which will be present in any real material, right? And indeed, if we describe the pendulum in terms of this multi-mode coupled system of which the center of mass is only one mode, then by the second law of thermodynamics, if we wait long enough, then the energy will distribute itself from the center of mass mode onto all the other numerous internal modes, and the pendulum will eventually come to rest, right? So now, depending on the specific material of this pendulum and the stiffness of all the other modes, this transfer of energy could take a very, very long time. This is the business of pre-thermal time crystals. You know, does this last forever, or does it just last a long time? But as a matter of principle, if you view this as a genuinely many-body coupled object, then this will eventually come to rest. Okay, so that's how the difference from a single mode describing the center of mass and a genuinely many-body coupled problem appears in this simple example. Okay, the second condition that I'll impose for the purpose of this talk is that my systems are non-dissipative. Okay, so indeed, as we saw in the last talk, as we saw in Jameer's talk, there've been many beautiful examples of driven dissipative systems or just dissipative systems where you can get very interesting phenomena. I just want to make a box around, you know, what is strictly quantum, what's strictly conservative. And I want to make a clear separation between the types of quantum time crystals that we'll talk about and kind of say battery operated clocks, right, which are of course ubiquitous, right? So just to make this very clean separation, our systems will be non-dissipative. And specifically for a driven system, like a periodically driven system like the ones we speak about, this means that this driven system should not actually keep absorbing energy from the drive, right? There should be some mechanism to prevent this system from absorbing energy, okay? And then, of course, the defining property of time crystals is that this is a many-body phase of matter which has long-range spatiotemporal order, right? So I want to define this as a crisp asymptotic phase of matter. I want to look in the limit of infinite sizes and infinite times. And in these limits, what spatiotemporal order refers to is that, if you measure a spatial correlation function arbitrarily far away, the system shows long-range order. And if you measure a temporal correlation function arbitrarily late in time, this autocorrelator will show you periodic dependence. Okay, so if you have a discrete time crystal, then it shows this kind of period doubling, period tripling, whatever you want. But in general, it would have to show you some kind of periodic dependence at arbitrarily late times. Okay, so really we want a many-body system which is non-dissipative and has long-range spatiotemporal order. This is what I'm going to mean by a many-body quantum time crystal. And as we know, using these definitions, it was shown by various people, and perhaps most crisply by Ushikawa and Watanabe, that within the context of thermal equilibrium or ground states of many-body systems, you can't have these types of many-body quantum time crystals. And indeed, this is what led to much of the work and much of the excitement on Floquet or discrete time crystals, which strictly lie outside the purview of these, which are many-body systems, which are strictly outside the purview of the systems that Ushikawa and Watanabe and Bruno, Nozier, and others were thinking about, right? So for a Floquet or discrete time crystal, again, I have in mind a many-mode, many-body system here. This Hamiltonian has a periodic dependence in time. The observables in my system are going to show you some kind of, they're going to show a subharmonic response. So if the system has a period t, observables will respond at multiples of that period. The most common example is period doubling, but in general, you can have any multiples of the driving period, or you can have time quasi-crystals where you can get kind of non-commensurate responses. You can have time glasses. There's multiple ways to break time translation symmetry, right? But we'll stick to time crystals. Okay, to define a phase of matter, we need the response to be robust. And indeed, this is where many-body localization comes in, because if you have a many-body periodically driven system, again, just by the laws of thermodynamics, you expect the system to actually heat up to infinite temperature, in which case the system is non-conservative and all correlation functions just look trivial. Okay, so many-body localization is necessary to prevent this heating to infinite temperature. And then we'll again look for this spatiotemporal order. Okay, so the most familiar model where this shows up is the model we wrote down several years ago by now, which is this kind of kicked Ising chain, right? So we have some Ising type interaction, and then we have a rotation about the x-axis. By tuning these parameters, if you have only nearest neighbor Ising interactions and this rotation, you can actually work out the phase diagram completely. You get a number of different phases, of which the time crystal is one phase. It's easiest to understand it in this limit of this perfect pi rotation. So indeed, if we fix this rotation parameter to exactly enact a pi over 2 rotation, then we have some diagonal z Ising interactions and a perfect flipping of the spins. So then, in this trivially gives you period doubling, right? Because if you start with some pattern of sigma z spins, then one period later that pattern flips and then it flips back and so on. Okay, so along this particular line, which is the pi over 2, the perfect pi rotation, you trivially get period doubling. And you also actually get glassy long range spatial order. Okay, so if you go in and you look at the way to very crisply define this is to look at the eigenstates of the Floquet unitary operator and to measure long range correlation functions in all the different many body eigenstates of this operator. And then you'll find that arbitrarily long range correlation functions will give you a non-zero answer, but that this correlation will be glassy. In general, it'll have random sign. Okay. So fine, this is well and good, but of course the interesting thing about this phase is that it's not just one fine-tuned point where I'm literally going and flipping all my spins, but rather this forms this robust extended phase of matter, right? So I can perturb away from that point in various ways. I can enact an imperfect rotation, so I can rotate not by perfect pi but by pi minus some angle. That's shown by this axis here. And the business of having a phase of matter is that even with those imperfections in the angle, my response should be locked at period doubling. And more generally, I don't have to have only Ising type interactions. I can add in all sorts of longitudinal fields, XY interactions, all of these different things. And this phase persists as a robust phase of matter, okay? I should say that the really special thing about this formalism is that this time crystal phase is a paradigmatic example of a new type of eigenstate order-based non-equilibrium phase of matter. Okay, so this is a new entry in quantum statistical mechanics and how we think about phases and phase structure. There was once a poll that one of my collaborators giving this talk did. He asked like an audience of experts in time crystals, how many of them had heard the word eigenstate order, and it was actually a very small subset. And this is really the key idea that allows us to crisply define this as a many-body phase of matter. One of the contributions of Oshikawa and Watanabe's work was that they were able to very crisply give a definition of time crystals and then show that that does not exist in equilibrium. So this eigenstate order, where you go and look at individual eigenstates of this many-body Floquet unitary and define long-range spatiotemporal correlation functions in those, gives you a similarly crisp way to define phases out of equilibrium and has crisp predictions for what the dynamical consequences of that eigenstate order will be. Okay, so good. So then, based on this kind of proposal to have this drive with dominantly Ising interactions and imperfect rotations, this is something that an experiment can easily do. You can prepare some initial state, see how it evolves under this type of drive. And indeed, there are kind of three experiments. There have been many experiments, but I picked the three that are kind of closest to this kind of proposal, right? And the two experiments that are most familiar are the ones in disordered nitrogen vacancy centers in diamond and trapped ions in one dimension. These are the 2017 papers. But actually, there was a different example just a year later on a spatially ordered, no disorder, no many-body localization NMR crystal in 3 dimensions. And all 3 experiments followed a similar protocol despite having very different setups, and all observed virtually indistinguishable signals. Okay, so if you had a superficial view of what was going on, you would have said that actually this problem was this corner of the problem was solved in 2017. We had a fancy Nature cover, everything. There's nothing left to do here, right? But actually, what we've done in the years from 2017 till now is to really go back and try to understand these experiments in detail and to see, what is it that they actually saw, right? Because they clearly couldn't have been seeing this kind of asymptotic many-body localized time crystal because, well, one of the experiments on this NMR crystal, it was a spatially ordered, perfectly no disorder, no nothing, ordered crystal in 3 dimensions. Okay, that's not a system that has many-body localization. So, here is the current status of the experiment based on what we've understood since the original publications. The diamond experiment, already in the title of our paper, that's an experiment I was involved in Misha Lukin's lab, we already knew that was not going to be an asymptotic time crystal. The interactions in the problem were too long ranged for it to be many-body localized. So it was what's known as a critical time crystal, which just means that the signal kind of decays power law slowly in time. Okay, so this was part of the title of the original paper. It was never intended to be an asymptotic time crystal. In this next experiment on the trapped ions in 1D, that kind of was as close to the theory as possible because it was in 1 dimension, it had disorder. But actually, it turned out that model also is an example of a prethermal time crystal. This is a prethermal time crystal of the variant that Elsbauer and Nayak wrote down in 2017. And the basic idea of prethermalization here is that the system for a very long time looks as though it's governed by some kind of effective Hamiltonian. And if that effective Hamiltonian has some kind of symmetry breaking, or approximate symmetry breaking, then if you prepare very low temperature states for that effective Hamiltonian, these can show order for a long period of time. But if you prepare high temperature states of that effective Hamiltonian, then those decay very quickly, okay? So this is an exact simulation of the exact experimental couplings in the experiment. And what we found while writing this review is that, some initial states, these are these polarized initial states or near-polarized initial states that were in the experiment, can show you this very, very long-lived signal. But actually, if you prepared other initial states, those that would be at high temperature, then those would actually decay very quickly, okay? So this experiment, despite having this disorder, actually also was a type of pre-thermal time crystal, and explain why in just a moment, okay? And finally, there's the most puzzling of the experiments was this NMR spatially ordered solid. And what we realized there is that the reason they were seeing the signal that they were seeing is because this was a type of pre-thermal U1 time crystal, is what we called it. And what that means is that the system looked as if it had a quasi-conservation of magnetization. So that's the U1 symmetry for a very, very long period of time. So if you measured a global observable like the magnetization, because that's approximately conserved, that looks like, it has this long-lived signal. But actually, if you measured local spatio-temporally resolved autocorrelators, which is what, the MBL time crystal wants you to measure, then you would see your signal decay very, very quickly, okay? So this is all to say that, if you just do experiments from a few, from one or two initial states, probing only one or two coarse-grained observables, you can actually get very different, very, very similar looking signals, even if the underlying physics is very different, okay? And one of the key questions that we have to sort out is the difference between a pre-thermal and asymptotic time crystal has to do with what happens at infinite temperature, right? But an actual experiment is never going to have a coherence time, which is infinite. An actual experiment is always going to be a finite time experiment. So you have to wonder, like, if you only have access to finite times in experiments, that's what this line is trying to show. And the difference between pre-thermal and non-pre-thermal is what happens at very, very late times. Then how do you actually tell those apart in a realistic experiment, right? And what this figure is showing is that by drilling into the physics of what causes that pre-thermal signal, you actually can distinguish them even within the constraints of finite experimental lifetimes. So how does this work? For an MBL time crystal, we know that, any initial state you start with, all the eigenstates of this Floquet unitary are localized. All initial states are localized. So any initial state that you start with will show you this kind of period double behavior for arbitrarily late times, okay? Whereas in this pre-thermal time crystal, where you're using some type of effective Hamiltonian and low temperature with respect to that effective Hamiltonian, some initial states, which look like low temperature, almost polarized initial states or near polarized initial states, which is what these experiments considered, those can show you a long-lived signal. But actually, if you started with just some random other initial state, you would see even within your experimental lifetime that your signal decays very quickly. Okay, so just by changing the initial states that you prepare and run in your experiment, you can diagnose an MBL time crystal from a pre-thermal one, even within the constraints of a finite experimental lifetime, right? And likewise, if you consider this pre-thermal U1 time crystal, which is this time crystal that was there in the NMR experiment, the reason that they saw that is because they were measuring a global Z autocorrelator. They were measuring the polarization for the entire sample, because that's what you can do in NMR. It wasn't easy for them to have spatiotemporally resolved correlators. On the other hand, and that was showing this because that global polarization was coupling to this global conservation law. But if they had measured site-resolved spatiotemporal correlators, they would have actually also seen a rapidly decaying signal. Okay, so what these experiments did, they're fascinating experiments and they're engineering feats. And what they've done in us trying to really understand the physics of each of these experiments is they've helped us sharpen exactly what experimental capabilities we need to realize a bona fide asymptotic many-body MBL time crystal. Okay, so it's not just like we want a system that can realize it, but we want it to also have capabilities that we can say that we realized it, right? So for instance, we need the system to be large enough and generic enough to actually probe many-body physics. We need the system to have a long enough coherence time so that we actually look at late time observables. It can't be infinite, but we need it to be at least long enough, right? And then, from what I was saying right now, to distinguish this time crystal from the pre-thermal variants, we need to have site-resolved observables rather than just global ones. We need to have the ability to tune and prepare different initial states. And then finally, for stabilizing MBL, we need our interactions to be short-ranged enough. These diamond experiments and the NMR experiments had dipolar interactions in 3D, which are just too long range to get MBL of any kind. And finally, this was the main ingredient that was absent in the trapped ion setup, is that we need disorder for this kicked Ising type model. We need disorder to be present in the Ising even couplings. If we only have disordered fields, then what happens is that over 2 periods, this disorder in the field can get echoed out. So the system effectively looks very, very weakly disordered, and then that's not many-body localized. Okay, so this was just, these are the different ingredients. And then we can go through and look at the 3 different experiments. And we find that actually, with present day capabilities, none of these experiments have kind of all the different features that you would like, okay? I should say that with the trapped ion setup, trapped ions are a leading platform for building these digital universal simulators. So you can try to get all of these different features, but this requirement of Ising even disorder, it actually requires if you have these different couplings, to get disorders in the couplings, you need to have extensively many lasers. And from an engineering point of view, it's certainly doable, and there's an active effort to do it, but it's challenging. Okay, it's not easy to do. So the main, so this was the motivation for us to look at this when we read about Google's quantum supremacy experiment, and we had sharpened this list of experimental, desired experimental capabilities. What we actually found is that Google's Sycamore chip, it's a superconducting based simulator. It's a 2D array, okay, but you can actually create an effectively 1D system out of it. This system, you have all these different qubits, and you can act with different gates to couple neighboring qubits. You have a gate set that they're using, and from the existing near-term capabilities of the Sycamore chip, what we found is that it actually checks all the boxes and meets all the requirements for you to for you to realize this phase. Okay, so I should say here that this. Yeah.
In order that you have some more questions. Thanks.
Okay. Yeah. So I should say that this, Sycamore chip really represents a culmination of, decades of, or at least a decade or 2 of effort in pushing the boundary in the development of these designer many-body quantum systems, and which are in this so-called NISQ regime, where we're pushing the number of qubits, we're pushing the error rates down, and while the quest to build a universal quantum computer is still far in the future, what this time crystal proposal on Google's device shows is that the possibility of actually just treating these systems as new experimental platforms for many-body physics, and using their modern day capabilities, not their capabilities of, this will eventually be a universal quantum computer, but the existing gate sets, the existing noise levels can already allow us to probe interesting physics, which no other platform can allow us to do. Okay, so specifically on Google's Sycamore device, so here is their chip, they have a natural gate set. These are these so-called transmon gates. And in this gate set, they have tunable ZZ couplings, tunable XX and YY couplings. We can make these ZZ couplings dominant. We can make disorder in the Ising interactions as we wanted. Then we can have all sorts of rotations, on-site rotations. So essentially, this idea of having dominantly Ising interactions followed by imperfect rotations exists in their current capabilities. Okay, so that's what we did. The details are not so important; those are there in our paper. But the point is that we can now look at a phase diagram based on the couplings that are present in their experiment, and we get a robust time crystal phase. And this is a genuine robust time crystal phase, which will show you all the different boxes, unlike the previous experiments. And then this can transition into different regimes, and you can use the simulator to study the properties of these phases, the properties of the transitions, all of this stuff, right? So coming back to our table, even with the existing noise rates in these platforms, you can look at signals for hundreds of periods. We characterize this carefully. This is 50 plus qubits, so it's not the millions of qubits that was there in the NV experiment, but it's more than the 10 or so qubits in the trapped ion experiment. The experiment has worked very hard to eliminate this kind of long range crosstalk. It naturally looks like nearest neighbor gates, so it's short range interacting. You can get this Ising-Even disorder. You can make site resolved measurements and prepare all sorts of initial states. Okay, so these are kind of snapshots of what you might see on this experimental platform. Depending on which initial state you feed in, you could actually just look at the state in time and see your time crystal kind of show you this glassy spatial order and oscillations in time. You would see your thermal phase quickly thermalize, and you would see your MBL paramagnet just preserve local memory without oscillating. Okay, so I'll conclude there, but as a broader outlook, I want to say that there's also lots of other questions on what we can do in terms of many body physics in this NISQ era. What types of new phenomena we should be exploring. The time crystal is one example, but actually a lot of work in quantum dynamics now considers quantum circuits, to explore questions on chaos, on thermalization, on hydrodynamics, entanglement dynamics, and we're really getting to the point where we can go from thinking about condensed matter experiments in near equilibrium settings of time-independent Hamiltonians to these much broader classes of quantum experiments which are natural on these digital simulators. So with that, let me thank my collaborators and stop. Yeah.
Thank you very much. So let's have time for a couple of questions. So Christoph, you go ahead first.
Okay, thank you. I would like to ask a question concerning many body and few body, or many body or many degrees of freedom, or few body degrees of freedom. In any time crystals, what we need a kind of integrability. Either it is local integral of motion in the many body localization case, or any other, let's say, type of integrability. And that also means that effectively the dynamics is always restricted to a few degrees of freedom, as compared to the, of course, entire Hilbert space. Otherwise, of course, we would have some kind of ergodicity and heating and so on. Do you agree?
No, I don't actually, because if you take this effective L-bit Hamiltonian for many body localized systems, it still has, yes, there are these local integrals of motion, but it actually still has interactions between all those local integrals of motion. And it's clearest to see this because if you look at entanglement dynamics in the problem, starting from some product state, what you'll find is that the entanglement grows very slowly. So it'll grow logarithmically in time, but it actually eventually saturates to a volume law state. So yes, there is ergodicity breaking in terms of local memory of the initial condition is preserved. But over time, the system still explores an extensively large Hilbert space because the late time entanglement entropy gets to a volume law, even if it grows very, very slowly. So having a volume law entanglement entropy, which is exploring extensive Hilbert space, is compatible with having local memory of initial conditions. So these many body localized systems are actually many body. And this is the main difference between Anderson localization and MBL, because if you look at entanglement dynamics, for Anderson localized systems, the late time states remain in area law because that's the non-interacting limit. But once you add in the many body interactions, it goes to a volume law. So I would say that they are still actually extensively many body systems.
Okay, thank you for your opinion.
Yeah. I have a short question I wanted to ask you. So I know that there is now a lot of fuss about using NISQ because obviously it has a lot of advantages. But nevertheless, NISQ is based in that you do quantum circuit, you have errors because there is no way to have errors. You have to correct it, okay? And then you have your result. So for some things, I think this is fantastic. But for instance, in the platforms that you were using, why is the difference of using, I will say, ultra-cold atoms, in which you don't have to correct errors, you have a many-body system, and it's highly so it's, of course, it's not universal, but nobody cares at this moment if it's universal or not. I would like to understand what is the point on using.
Yeah. So here the point is just that to see the space, we need these different conditions. And the only, so the main thing that presents an obstacle with your usual, like, we thought a lot, we actually worked very hard in thinking, and discussing with Emmanuel Bloch on his systems of Bose-Hubbard systems and Fermi-Hubbard systems, the type of model that you need. So of course, lots of interesting simulations are done on cold atom systems, right? Specifically for the time crystal, we need this kind of dominantly Ising interaction and Ising even disorder. And this is hard to do on any of these cold atom platforms, except for Rydberg atoms. So Rydberg atoms actually meet all of these requirements because the Rydberg interactions are short range. It's 1/r⁶. They look like Ising type interactions. You can do these rotations. So they meet all of these requirements, but currently they're only limited by coherence time. Okay, so we actually spent nearly a year trying to get this experiment to work in Emmanuel's lab, but it's only 10 periods or so. So, indeed, so, if in the next 5 years their coherence time gets to hundreds of periods, then we're fine. Yeah. I mean, and the Google experiment, we're not actually doing active error correction yet. So the effect of noise that we have will show up in terms of a decaying signal, but we can characterize this decay very well because the noise is being calibrated very well. And then we can use that to understand what kind of lifetimes we would get. And, it's still a few hundred periods.
Yeah. But in any case, you have to calibrate the noise every time and so on. But
of course. Yeah.
Right. So thank you very much, Vika. That was very nice talk. Let's move to the last talk because we are a little bit late. So I have horrible chairperson, as you can see, already late. So
thank you.
If there are other questions, which I know, please use the chat to ask Vika. And thank you again to be here at this hour of the day for you, which is quite late. Appreciated.
Yeah, thanks.
So let's go to our last speaker of this first session, which is Modeyev Segev, which is going to talk about photonic time crystals. Correct?
Yes, absolutely.
Good morning.
Good morning, Anna. Good morning, everybody. I know that I appear on your screen like Victoria, but this is because I lost the Zoom link. But this is live, and I have to manage with it. Just a moment. Let me adjust everything, and also to see that I can see the pointer. Okay. So I'm going to talk to you about something completely different, which is photonic time crystals. It has nothing to do with many-body quantum. It is completely classical, completely Maxwell, with a taste of quantum under spontaneous emission and stimulated emission and Cherenkov radiation and all kinds of stuff, which in my opinion, if you will see it right here, it is the area that is about to explode in photonics. Trust me, 2 years from now, there will be hundreds of papers on this. Hopefully, we'll have the first ones, the first experiment. So the idea is really to have some dielectric material that you change epsilon a lot by a large amplitude very fast in time. And
sorry,
yes?
Moti, sorry, can you put the slide form? Because it appears small. I think you should put a display.
Just a moment. I think on display settings, I need to change something. Huh?
Display.
Is this better?
Well, yes, better. Thank you. Yes.
Okay. So thank you, Anna. So let's move a little bit. So first of all, the Technion team are my students, Eran Lustig, Jonathan Sharabi, Alex Dikopoltsev, Mark Lyubarov, and Yaakov Blumer, who is now in the industry. So the idea is as following. When you think about a crystal, any crystal, what you really think of is some repeating structure, some repetitive structure in space or in time. It has a band structure with forbidden band gaps and so forth. And when the crystal forms spontaneously, like many crystals in nature, they also form spontaneously, then you have spontaneous symmetry breaking. But sometimes you can have it artificially. As we know very well, photonic crystals, even though they exist on some butterflies, we actually fabricate them in the lab, ordinary photonic crystals. So I'm going to talk about a photonic crystal of different kinds, photonic crystal in time. Okay, so for example, photonic crystals in space are structures 1D, 2D, or 3D, where the scale of the photonic crystals, the periodicity is on the order of half a wavelength or larger. And what happens is that to get a full band gap in a photonic crystal in space, what you need is a contrast of the refractive index on the order of 1, usually about 2 or 3. This area exploded in 1987 with a seminal paper by Eli Ablonovich, who predicted that if you have a photonic crystal in all 3D for both polarizations, then you'll have inhibition of spontaneous emission. That paper is considered a field opener and has 18,000 citations in Google. Okay, so what I'm going to talk about now is about photonic time crystals, which means that the epsilon is changing in time in a periodic fashion, breaks time translational symmetry. The band gaps are in the momentum rather than the energy. The system conserves momentum, does not conserve energy. And really what matters is that the time scale and the magnitude of the modulation. And I'm going to try to cover some of these topics. We are active in all of them. Topology of photonic time crystals, bands, as you'll see, they are topological, all of them. Spontaneous and stimulated emission. In other words, we took the question that Eli Ablonovich asked for spatial photonic crystals into time crystals. And you will see that the answer is fascinating. Then we look at Purcell radiation, or better call it Cherenkov radiation, or radiation interaction with free electrons in this kind of a photonic time crystal. And experimental realizations, we are well on our way. Probably I will not have much time to talk about systems, photonic time crystals containing disorder and localization, but we have a paper coming up in PRL exactly on this, on the theory of this. So let's go first to the very basic, time reflection and refraction, okay? So let's look first on the spatial interface. Spatial interface means that here you have some material with epsilon 1, and then you have something with epsilon 2. So comes a wave. What happens to this wave? The wave now is reflected. Some of it is refracted according to Snell's law, and some of it is reflected, okay? And we all know Fresnel reflections and everything. Now let's assume that instead, what we have now is a temporal interface, which means that the material is completely homogeneous in space. Translational symmetry in space imposes that conservation of momentum. And then at some point in time, you change epsilon abruptly, like a wall, okay, like an interface. So what happens now, you again have time reflection and time refraction. But since, unfortunately, we cannot come back in time, at least I have not yet met anyone that came back in time, the time reflection is in space. It is caused by a temporal wall, but causality imposes that you cannot come back in time, but rather it is reflected in space. Okay, so the implication is exactly as I've drawn. So in other words, you back reflect in space. So you have two things. One of them is refract, which I will show you in a few minutes that you will have the refracted wave will have a different frequency, and also back reflect in time, which will change the frequency and also reflect back in space, because it is caused by a temporal change in the refractive index or in epsilon, but we cannot reflect back in time because of causality. So that's the idea. Now, so far, I will tell you that what was done in experiments so far is time refraction has been shown. It is really not extremely hard to show it, but it was shown only lately by several groups. The first one, I think, was Bob Boyd from Ottawa. But time reflection was shown only with water waves and in transmission lines. So what you see here is a very interesting experiment that my friend Matthias Fink did it, where he dropped it. He created a wave by inserting some little statue of the Eiffel Tower, and then dropping the water tank. And what you saw is exactly this, that the waves went out and back by the time reflection. But the rules of the game are completely different fundamentally between water waves and electromagnetic waves, if nothing else, because we are talking about tensor waves, polarization, and so on. They make a big difference. Anyway, but in electromagnetism, time reflection has yet to be demonstrated. It has never been observed. So in order to create a crystal, what we need is to take these walls or these interfaces and repeat them periodically. Okay, so in a spatial lattice like this, let's say make a multi-layer system or a one-dimensional photonic crystal, comes a wave, part of that is reflected, part of that is refracted, and we have the Fabry-Perot resonance that we all understand and so forth, which really also talks about band gaps and so forth. In a time lattice, now we are talking about an incident wave, and now you change epsilon in a periodic fashion. You can do it in a cosine way, or you can do it in a stepwise function. either of them will do the same thing. And what you will see in a moment is that what is conserved now, because the material is completely homogeneous, is K, the wave, the momentum, which means the wave number. And as we'll see in a moment, there are some fundamental aspects having to do with the dispersion curve. So what does it mean? If you look at the modes, then what you find the modes here is that the modes here, we have two kinds of modes. One of them diverges to this direction, the other one diverges in this direction. But the diverging tails have infinite energy. Therefore, what we get is something that is localized in the bandgap. But here, it is really not the issue. You always have something that blows up exponentially and also decays exponentially in the bandgap. What really determines what you will see is causality. So we can talk today about a spatial lattice, a one-dimensional photonic crystal, or a time lattice, or something combined. Okay, and they will have something that is completely different. I'll come back to the band gaps. But if you want to look at what happens in a one-dimensional photonic crystal in space, what you have is band gaps in energy. In other words, there are frequencies of the photons for which you cannot have, nothing is transmitted, everything is reflected. Okay. In a temporal lattice, in a one-dimensional time crystal, okay, photonic time crystal, what you have is band gaps in momentum, which means that waves that are coming here are exponentially amplified and also is exponentially suppressed. Those that are suppressed are there, but they are not very interesting. It's like any band gap. But those that are exponentially amplified are extremely interesting, especially when you talk about vacuum fluctuations, spontaneous emission, and so on and so forth. And you can have something mixed, which is also interesting in itself. Okay, now let's see what happens now when you take a pulse and launch it into a photonic time crystal. I remind you, the medium is completely homogeneous, so momentum is conserved because of translational symmetry. And let's start by looking at the central K, momentum of the pulse, in the band. In other words, it sits somewhere here. And let's see what happens. So as you launch the pulse in, now it enters the material, it splits in two because it experiences time refraction and time reflection. Okay, it splits in two, it goes in opposite direction. And the time it experiences the other interface, it splits in two again. So what you get is the first two split, and then the other two again split. And there's interesting physics in there too. But let's see what happens now in the gap. When you launch something that goes in the gap, it is exponentially amplified. Now, if I make this time crystal very, very long, what you will see is that light stops completely, the pulse stops on its spot, and the amplitude goes blows up exponentially. Okay. Now let us see now again go back to dispersion curve and let's see what happens. So we calculated the Zach phase for the bands. Now why is that? This system really, the way you have some pulses, now that you change epsilon in a B-modal form. In other words, you change it from 1, 3, 1, 3. Let's say as a square wave. It doesn't. The shape doesn't matter much actually. Then this resembles a diatomic lattice. A diatomic lattice, everybody that is doing topological insulators or topological physics in large knows that this is the simplest topological system, which means that this really reminds us of the SSH model, the Schiffer's Higger model, and it has topological edge states. There's no topological transport in this because it's just 1D, but it's still nonetheless interesting. So that motivated my students to go and look and calculate the 1D analog of the Berry phase, which is called the Zach phase, in this one-dimensional topological system and look at the topology of the bands. Okay, and the numbers of the Zach phase are written here. Now, what does it mean? Okay, these Zach phases. It means that if you look, let's say, at this band, okay, this part of this is winding, which means that it has a non-zero topological geometric phase. Again, you can see why. You can see that if you go around the Brillouin zone, you undergo a twist here and a twist here. So it's winding. On the other hand, this one doesn't. Now, this has interesting implications when you go and launch a pulse into it. And for example, one of the implications now is what happens now here, and the splitting between the light, the pulse that is refracted and reflected is determined by this topological phase, the Zach phase. In other words, repeat the same experiment as before and just launch the pulse either in this band or in this gap or in this gap or in the bands, okay? What will happen is that the relative phase between them, between the refraction and reflection, is determined by the topological geometric phase, the Zach phase. Okay, the next thing that we looked here is what happens on the, okay, what happens at an interface. So we made an interface between two photonic time crystals. The first one is associated with the gap, with a band of that has a phase shift, exact phase of pi, and then after that a trivial band. Let's say this is the first and this is the third. Okay, so band in the dispersion curve that I showed you before. So now we launch a pulse and we ask what happens. So what happens now, you've created a topological edge state, an interface state, very, very similar to the edge state of an SSH model that we know from one-dimensional topological systems. And here it looks, here is how it looks. It stays, it is localized, it gets stuck on the temporal interface, and here the amplitude goes exponentially. Okay, so if I make this crystal longer and this crystal longer, the amplitude here will exponentially grow with the size. Okay, so the next question that we ask, there are many questions, some in classical, some in quantum, but here I want to focus on light-matter interaction. So the next question is really, let's take an atom and put it in a photonic time crystal. What will happen to it in the band and in the gap? And the basic question is, would spontaneous emission be suppressed, like Jablonowicz found in a spatial photonic crystal, or amplified? Because here the modes, the Fluke modes, are diverging. And then you can ask also, what is the lifetime of an atom in the excited state? Will it be prolonged or not? And the next one is really interesting in itself, because here, as I will show you in a moment, the spontaneous emission here will be amplified, or the vacuum fluctuations also, both of them will be amplified exponentially, not drawing power from or energy from the atoms, but drawing energy from the modulation. Okay, so maybe you can actually design a laser where the laser perhaps starts by vacuum fluctuation or by some seed from an atom or from a dipole that radiates, but later on the energy, everything is amplified exponentially, and the energy actually is drawn from the modulation, which does not have to be electromagnetic. It can be anything. Okay, it needs to be fast. There are some conditions, but you don't need light for it at all. Extremely interesting. Why? Because it's non-resonant light-matter interactions, and you can make a laser that is tunable over many wavelengths, irrespective of the frequency. Okay, so I want to start again with Jablonowicz. So this is a seminal paper in 1987, when what he said practically there is the inhibition of spontaneous emission. And then there was a race for people tried to do a threshold-less laser, and they tried really to make just the laser is sitting on a defect mode. And because all the spontaneous emission goes to that one mode that exists in the system, that defect mode in the system, then the laser will be threshold-less. Okay, and this was the first 2D one was done by Amnon Yariv and his student Oscar Painter, today a full professor at Caltech also. And the 3D one, to my knowledge, the first one was done by Noda in 2000. Okay, and what we're asking is, what will happen to spontaneous emission in photonic time crystals? So actually, this is a quite hard question to solve. So I want to draw again to the analogy. So in a special crystal, we have now symmetry with a unit cell in space. So the wave equation that describes it is written here. I wrote it specifically in this form so we can compare the magnetic field in both of them, which is simply easier to solve. The modes here are Bloch modes, as we know very well. The dispersion curve are what I've shown you earlier. Now, when you look at the time crystal, the equation looks similar, but it is not the same. Okay, notice the derivatives here in time, derivative here of epsilon times the first derivative. The eigenmodes are now Fluke modes, and the dispersion curve, which means that they are periodic functions with the periodicity of the modulation. The dispersion curve is rotated by 90 degrees, but there are additional spice to it because, in space, you can deflect from x to minus x, but in time, it would be nice to back reflect from t to minus t, but unfortunately, it doesn't happen. Okay, so what's the implications for radiation sources? So let's start classical to get intuition. So we put the wave equation now, and let's put the wave equation now with a source that is a plane wave with a particular k as a function of time. Okay, and to solve this, what you need is to find the green function. So we want, first of all, to find what happens to this plane wave when the illumination here, or the periodicity here, is like a flash. Once, boom. And you solve it, and I can tell you that the eigenmodes in the band here will look periodic, and in the gap, we have two of them. Both of them are physical, exponentially amplified, exponentially suppressed, exponentially decaying. Okay? The important one is the one that is amplified. Now let's take this radiation source, okay, and put it, and let's try several cases. So the first one, look at point dipole. Point dipole means that you will really look at the superposition of all the plane waves that constitute a point source. But let's say diffraction limited, so plane waves, so the size will be half a wavelength, okay? Then what will happen is let's put it in several cases. Let's put it on the band, let's put it off the band, and then let's put it in the gap. Okay, we do the same thing then with an extended dipole. Okay, the results are essentially the same. Okay, so it doesn't matter which one, some results are the same. So point A here on the dispersion curve, you see this is the band gap and this is the band. So point A here is on the band. Point B is off the band, so there will not be phase matching. And points C and D are in the gap. Point C is on the dispersion curve in the gap, and point D is off the dispersion curve in the gap. So what we see is like this. What we see is that if we look at the points A and B, which are on, A is on the dispersion curve, the energy grows nicely, grows, okay. B doesn't grow because it's not phase matched, which means that what you are looking now is that the radiation source is not phase matched with the modulation. So therefore the exchange energy and the amplitude remains always small. But the more important one is really what happens in the gap, because in the gap, point C and D, one of them on the dispersion curve, the other one off, both of them, the energy of the electromagnetic field that is generated, here we're talking about radiation field, classical, both of them are exponentially growing. And what you see here is the log of E. This was a linear scale, here is the log. So you see they are exponentially amplified. Yes, you can see some modulation. The modulation is not important. The exponent of the growth is irrespective of the frequency. It doesn't matter if you're where you are on the dispersion curve or not. So the next thing after that is to say, okay, we did it classical. Let's see what happens quantum, because spontaneous emission is really a quantum phenomenon. So the way to do it is actually quite tricky. It also has quite a few months to find the correct Hamiltonian. You need to start with the eigenmode equation, find the Lagrangian, find the Hamiltonian, then do second quantization. And then after that, at the end, the very end, you get the Hamiltonian for this. And the important part is actually not this. This is the usual part of the Hamiltonian due to second quantization. The only thing that is interesting here is this, but it's just a coefficient. It doesn't matter so much. The important one is this. The important one is that you have generation of two photons simultaneously, one of them with K, the other one with minus K. Okay. And now let us put inside it an atom or an atom in the excited state and ask what happens. I will not show you all the calculations. You have to believe me that they are correct, but I will tell you that there are three basic cases, and there is correspondence, nice correspondence between classical and quantum. Okay, so there are three ones. They are oscillating, linear growth, and exponentially growing. The oscillating one, when you are off the dispersion curve, there's no phase matching, and as we saw in the classical case, it's just the source of radiation. The atom will exchange photons with the field, practically, with the photon, the population of the field. Then if you're on the band, the number of photons grows linearly. It's a very interesting effect because what you have is really some chain where you exchange photons, some of them are reabsorbed and re-emitted. There's a whole scheme here. And in the gap, they're exponentially growing. Exponentially growing means that the number of photons in a mode is growing, is amplified all the time by the modulation. Okay, the difference between so the fundamental difference between spontaneous emission or emission in general in a photonic crystal in space and photonic time crystal is really energy conservation versus causality. In photonic time crystals, energy is not conserved. In other words, the frequency changes because of the modulation. So the way to think about this, think about the capacitor where you change epsilon. So what happens when you do that in a capacitor, you change the stored electromagnetic energy. Same happens here classically, same happens here also quantum mechanically. So you have quantum fluctuations that start from the modulation. So you can trigger the population and the modes either by quantum fluctuations, or you can trigger them by an atom in excited state. The dipole emission always exponentially explodes in the gap, regardless of frequency. The spontaneous emission in photonic time crystals which is also an interesting, fascinating effect. Now, if you sit on the dispersion curve, I'll show you maybe on the previous slide. Okay. Okay, let's look at the quantum picture of what happens when you are sitting right here and you are getting from point A close to the band edge. Okay, and you solve the quantum Hamiltonian now. Okay, so what happens here is actually as you get closer and closer and closer to the band edge, then the lifetime of the atom becomes extended and radiation is suppressed. But then as you cross a little bit into the band gap, everything explodes. You get exponential amplification of the number of photons in every mode. And as a result of this, the radiation field explodes. The band edge is most probably an exceptional point because it converts from something that slows down by virtue of the dispersion relation here and actually the density of states, of momentum states, into something that explodes exponentially. And because of that, we think about constructing a proper resonator and selecting the preferential mode that will lead to photonic time crystal lasers. Now, we also looked at what happens to free electrons, which is Cherenkov, or if you wish, Purcell effect. And what we found with the same Hamiltonian, only now we have also this, we have this term, which is now for free electrons. And we ask ourselves what will happen. So we found three types of photons that are emitted. Regular Cherenkov photons, momentum gap photons, and then also the photons that are emitted naturally, something similar to the Purcell effect, okay, that are by the periodicity in time. And they actually interfere. You want me to finish in a minute? I will. Okay, so they interfere, and we found two regimes. One of them is that the free electrons emit radiation. The free electrons emit radiation in two regimes. One of them is above the Cherenkov threshold, and also below simultaneously, and the radiation is emitted forward and backwards. And if you are looking at the band gap, if the momentum, if you look at what happens to the photons that are in the momentum gap, their amplitude is increased exponentially. In other words, the number of photons is increased exponentially in the quantum picture, and the quantum picture gives not only enhancement but also anti-level crossing. I want to say maybe 2 slides on experiments. Okay, now to do everything that I told you, it is not magic, but it has 2 stringent requirements. One of them is that the modulation must be comparable at the rate of the electromagnetic waves that propagates in the medium. Okay, so if you want to look at waves, let's say in near infrared at around 1 micron, you will need to be able to change epsilon on the order of a single femtosecond. Not only that, you need to change epsilon on the order of 1. So until recently, it was impossible, but now it is possible. The idea is to use materials that have epsilon near 0. And what you can see in a moment, never mind how we do it, what you'll see in a moment is something that we observed in experiments. And we are looking now at something where a probe beam is 1,300 nanometers near infrared. And we use a pump beam that what it does, it illuminates the material homogeneously, uniformly everywhere. And it has a very short pulse of on the order of a few femtosecond, let's say 5 femtosecond. And we see rise time that is shorter than the oscillation, than the time of the pulse that triggers it. Extremely interesting. It is smaller than 4 femtosecond, which is our measurement device. Okay, so in other words, and the change in epsilon is on the order of 1. And here this is my last slide, and I will say that in my opinion, even though they are not spontaneously forming, at least in the linear case, in the nonlinear case, they will also spontaneously form like solitons, as we know very well from nonlinear optics. But in the linear regime, they are not spontaneously forming. Still, there is a lot of new physics on light-matter interaction, the exponentially amplified spontaneous emission in the momentum gap. We have many new features on Cherenkov for cell radiation, topological aspects, and interaction with disorder, which is something that we have a PRL coming out with the theory of that. And let's hope that within a year, we will be able to demonstrate the first photonic time crystal. Thank you, and I'll be happy to answer questions.
Thank you very much, Moti. There's a couple of questions. We have time if we go a little bit fast, so please, Ishar.
Thank you.
Yeah, a little bit fast, please. Yeah.
why the spatial crystal and temporal crystal is so called? Is it because of that there are occur spatial and temporal coherence in it? Secondly,
wait, I did not. Just can you repeat it, because I did not. I was not able to understand the speech. Something is wrong with your Zoom, I think. Maybe you can repeat it slowly.
Okay, sir. Why the spatial crystal and temporal crystal is so called? Is it because of the spatial coherence or temporal coherence? Secondly, my question is about the Hamiltonian. Which type of symmetry you have used to find the symmetry, the Hamiltonian?
Okay, so the first answer, if I understood correctly the question, if you ask me about coherence. Now, keep in mind that the photonic crystals, yeah, if I understood correctly, Anna, did I understand correctly the question?
Well, it was also difficult for me to understand, I have to say.
Okay, so it was, so if I understand correctly, the question was, is it how we, is there any requirement of on coherence? So the answer to that is that what you need is coherence of the modulation. The modulation needs to be periodic in time, okay? But it does not have to be another, it will have a Fourier spectrum. So if you make the Fourier spectrum, not really stepwise, but something that changes adiabatic, let's say a bit inclined, all the physics remains the same. The key issue is that it cannot be slow. It cannot be slow. If the modulation is, instead of having like a wall in time, if it is slow and it includes, let's say 10 periods of the electromagnetic waves that goes in the system, then the time, the band gap will be diminishingly small and you will not see anything. This is, so really what's important is how abrupt is the modulation. It does not have to be a step function, but it needs to be sharp. Okay, that's the first one. The second one regarding the Hamiltonian. Well, what we did, we really followed the steps that we teach in quantum mechanics too. And the symmetry that we used here, the eigenmodes are momentum modes. This is really the important part. And from there, we found the Fluke eigenmodes, because what you have is periodic symmetry in time. The medium is completely homogeneous in space. And the trick was really to understand, first of all, from intuition, that because you must conserve momentum, you have no choice but to to generate two photons at every instance. So you emit a pairs of photons, k and minus k, because the system must conserve momentum. That's the trick. And we are writing now the first paper on this business, and there we will see all the derivation. It's tedious, but the intuition is actually simple. It's just what I told you now.
Okay, thank you, Moti. Thank you very much. I'm afraid we have to stop here. There is a break now, so maybe you can ask Moti personally now, because it's already 12 minutes after the break. And so I'm afraid that we run a little bit of time. Okay? So
we resume in 20 minutes. 20 minutes, we start with Andreas Nunekamp. See you.
Okay.
Thank you, Anna. Best regards to Maciek.
Thank you, Moti. Thanks.
Professor Silverberg, can you hear me?
Yeah. Should I try sharing my screen?
Yes, please. Thank you.
Okay. So, can you see?
Okay, I can see it. Launch slideshow mode.
Slideshow mode. I should then share a different screen. 1 second. Mhm.
You already started the sharing.
Yeah, I started, but then I had to unstart in order to show that I can share my screen here.
Okay.
And can you see my laser pointer?
Yes, perfectly. Do you have audios or videos in the presentation?
No, I only have an animated GIF. This should work. This worked
Okay.
in the past. Yeah.
Thank you very much.
Thank you. How do I now?
Andreas, I think you can start sharing the screen.
Yeah.
Well.
Hello, Andreas.
Hello, Anna.
So that works perfectly. That's very fine. So the idea is, I'm sorry, because sometimes I don't like to interrupt, so it's better if I don't say anything. But the idea is this 25 minutes talk plus 5 minutes question. So this morning it didn't work exactly like that, but let's try in the last 2 sessions.
Yes, yes, let's try.
The time.
Yes.
So there is still people entering. So let's start. So good morning, everybody, again. It's my pleasure to chair this last session in the morning, which is starting with Andreas Nunenkamp, which is going to talk time crystals beyond the MLB. So please, Andreas, whenever you want, you can start.
All right, yeah, thank you, Anna. Good morning, everybody. So let me first start by thanking the organizers for putting together the conference, really reflecting nicely the breadth of the field. So it's very nice to bring people together on this topic, coming from very different directions. And then let me first introduce my collaborators. This is, of course, first and foremost, Andrea Pizzi, my student at Cambridge, who did all this work, and my collaborator, Johannes Knolle, who a former colleague of mine now at TU Munich. All right, so let's look at the menu today, what I've been want to talk about. And I want to start with something which is supposed to be familiar to most of you. I want to connect to what I will call the MBL many body localization paradigm. So to period doubling in disordered spin chains. We've heard a little bit about this morning from Vedika about this. And but then I will really focus for the bulk of the time on this paper here of ours. So higher order and fractional discrete time crystals in clean long-range interacting systems. And if time permits, I will briefly say something about a slightly earlier work on time crystals and quasi-time crystals in ultra-cold bosons. But without further ado, I will just start setting the stage. And like with the other speakers, it's nice to just flesh out and say what we mean here. I will be focusing on discrete time crystals. So these are non-equilibrium phases of matter that break the discrete time translation symmetry of a periodic, so AKA flow K driving. And more technically, this was nicely fleshed out, for instance, in a paper of Saros here. There's a local observable with a quantum expectation value, f of t, so that in the thermodynamic limit and for a set of initial conditions, we have the following properties: discrete time symmetry breaking. So although the Hamiltonian repeats itself after a time big T, the period to big T, we don't come back with our expectation value of the local observable at this period. And this response, the subharmonic response, is really not only fine-tuned in the parameters, but it's very rigid. So these oscillations do occur even if I change slightly the parameters in the Hamiltonian and perturb the Hamiltonian. And third, there should be persistence. So this kind of subharmonic response should extend to infinite times. So as you know, has come kind of out already in several other talks, the devil is of course in the details, and we will revisit some of this now as we go forward. One thing which is pretty clear with talking about a many-body system with interactions, And this in a setting where we have flow K driving, so periodic driving. So the Hamiltonian is time periodic as written. And then very generally, we have to face the scenario of heating to an infinite temperature state, which does happen very generically. And so how to avoid this, which is sometimes called heat death. And there's, Norman has also fleshed out several categories how to avoid this. Here's my version of saying this. You can throw in disorder into your problem, then disorder and interactions together may lead to a phenomenon called many body localization, and that might be a source of non-aggregaticity, and on which you then can build a time crystal, discrete time crystal. And many papers do that. A second option is to use dissipation. Here's an example from colleagues from Nottingham looking at this, also a very natural scenario. So where you're trying to remove the energy which is added and entropy to come back to a non-infinite temperature state and stabilize an interesting non-trivial response that way. I will focus on a scenario which is based on long-range interactions. And I thought Norman would have talked this morning about it, but he changed his mind at the last minute. So long-range interactions can lead to pre-thermal phases, and that's the setting I will be talking about most. But before doing that, I will just start us off with a very familiar one, namely going back to these seminal papers talking about an MBL-based 2 DTC, n equals 2 DTC, also known as pi spin glass. So the setting is an interacting spin chain, spin 1/2 chain, in the presence of a transverse field. In one of the version of this, there's binary driving, so you divide the period of your driving into 2. There's a first half where you do a spin flip on all the spins, and the second part where you combine interactions and disorder to stabilize that response. And very schematically, what happens is the following. So you can start out and understand this from an integrable or trivial point. You switch off the interactions, you go to a perfect spin flip. Then in pictures, this looks like this. So you start with, you have initial condition all up, then the spin flip drives all down. After one iteration, it goes all up, all down. So the magnetization shows these oscillations between +1 and -1. It's a period of 2 relative to the driving period of 1. So that is the core, the starting point for your DTC response. The frequency is at 1/2 of the driving frequency. But of course, that's trivial in a certain respect, just the starting point. You see that as you start to make the spin flip imperfect, so you perturb the system, you go away from this point, and you add a bit of epsilon into the driving field, then you start to see that, again, pictorially here, you start all up, but then you start to rotate around the spin in all kinds of directions, and this particular response is lost. Now, the non-trivial bit is that this this integrable point can be made more rigid by turning on the interactions, or here interactions and disorder, and you end up with all up, and then you start to make these errors, these mistakes, but the interactions do then counteract and stabilize a response at half the driving frequency. And it's this kind of subharmonic response we're looking for, which is robust to perturbations, and it then later on as a second criterion persists for infinite times, which you can't see from these pictures here, even if they're just pictorial. One nice way to look at it is you can calculate the Fourier transform of this magnetization and plot it its as a function of frequency and of this mistake of this driving field, or driving strength. So this is where your interaction is off. You just have one point where there's this response at half the frequency. And if you turn interactions and disorder on, then there's a whole plateau. And this plateau means that the response is robust to these mistakes. Again, this is here just pictorial. So that just sets the stage of what I would want to say now. Namely, I want to focus now on a setting which is in many ways different, but also shares a lot of this kind of physics. So let me introduce our model we've been thinking about. It's a spin chain, spin 1/2, It's in a magnetic field. The crucial difference to before is that here we're dealing with long range interactions, and that's what's going to drive the whole difference. In fact, I will start to actually from a simple limit, namely from the limit of all to all interactions. So as indicated here, we have spin 1/2. This is this sigma ij, and it's coupled all to all. The spin flip is indicated here by the second term. And you see in this paper, we're mostly focusing on continuous periodic driving in contrast to many of the other schemes which are thinking about binary driving. And we think this is experimentalist friendly. We have looked also at the case where there's binary driving and it works just very similarly. This interaction term of all to all or a collective spin is very important in the following. So this is an LMG model, Glick model, and it allows us crucially to have a semi-classical limit to the system. I will comment on going beyond this limit of collective spins a little bit later. The key message I want to say out first is that this clean, so no disorder system, spin 1/2 system, sustains a whole zoo of different higher order NDTCs. So with integer and surprisingly even with fractional n's, and n being larger than the local Hilbert space dimension, which is 2. If I then move on to beyond the LMG limit, these will be arguably pre-thermal states. So that's my main message. Let me now walk you through what we actually did. How do we study this system? As I just said, this in the simplest case is an all-to-all, a collective spin system. So we can make use of the Schwinger mapping of a collective spin of an angular momentum to a Bose-Hubbard dimer, so to 2 bosonic modes, which I call here spin up, spin down. These are bosonic creation annihilation operators with up and down. So our Hamiltonian maps onto this kind of problem where we have not n spins, but we have n bosons in a double well, which are moving, feel a on-site interaction which is the first term here. The interaction term turns into an on-site interaction between the bosons. And the second term, the spin flip term, turns into a tunneling for the bosons between the 2 wells. As you may know, looking at n bosons in a double well potential can be done, the exact quantum dynamics can be done very efficiently and even for hundreds and thousands of bosons. So that gives us one handle to do exact crystallographic findings as to the symmetric part of the many body space for the spins, allows us here to do efficient quantum dynamics. And furthermore, it gives naturally rise to a mean field limit. So if you increase the number of bosons, you come to a regime where the Gross-Bitievsky equations become exact. So these 2 here, these are coupled nonlinear equations, which you can easily integrate for long times. So that's the background, what we use most of our methods. Let me now walk you through what we see. So let's start from the simplest state with all spins up, and look at we're going to look at more general states a bit later, and study the dynamics of magnetization, which is in the collective spin model is the line to the z, and in the bosonic language, it's the number difference between the 2 wells. So here is if you don't have any interactions, then you expect this dynamics at stroboscopic times at least to be of a cosine, and its frequency is linear in age in this driving field. So if you plot the frequency as a function of spin flip strength, you would expect straight lines as here. Now, if the interaction is turned on, this becomes very rich. So you end up with a very rich response. This is the magnetization, the Fourier transform of the magnetization of this system. And you can actually nicely identify all kinds of dynamical phases here. There's a a macroscopic self-trapping for the bosons. There's the 2 DTC, a 4, 3, 4, 5, 6 DTC. You can zoom into these regions here and find higher orders even more. Or here you find various fractional orders. And my message is here really that these plateaus here, that means that the NDTC response is really robust to finite detunings, finite changes in the spin flip strength. And you see that many of these responses are, some of which are higher order, meaning that n is larger than 2, and some are even fractional, as like they are not an integer number. This kind of semi-classical mapping, I talked about the magnetization before. There's a second variable which is important, which is a phase. So if you think about the collective spin, it has a Z projection as well as an angle on the Bloch sphere, and these two characterize the state of the dynamical system. This kind of looking at its semi-classical dynamics is very useful and can characterize the system very well. So here is I start out where here is the initial state of the system, and now as I go through the various stroboscopic times, I see the various red dots up here, and I remain close to magnetization 1. That's a self-trapping regime. This is how a 2 DTC looks like. I start again up here where the green star is, and now I start to jump every time every period I jump between two islands, which are called here 0 and 1. Up here, down here, up here, down there, up here, down there, and so on. So these kind of semi-classical Poincare maps, which we have seen in one of the talks before on Monday, provide a very intuitive picture of this type of dynamics. Now let's move on to something a bit more exotic then. So the 4 DTC, what does that look like? Well, you might imagine, so as a function of time, the magnetization, the stroboscopic magnetization goes 1, 0, -1, 0, 1, 0, -1, etc. You have a response at a quarter of the frequency of the driving frequency. And again, if you look into the Poincare map, it looks quite nice that you have these islands, which are labeled here 0, 1, 2, and 3. And the system dynamics moves us every time period between these islands, returning to the original one after 4 steps. You also see nicely that the original Hamiltonian didn't have a Zn symmetry, so it cannot piggyback on any of that symmetry of the Hamiltonian. But it's really generally breaking this. So you can go on, you can look at n equal 8, and I want to just show the difference between what is 8 DTC and 8/3 DTC. If you're 8, you believe me now, or you can imagine that this is between 8 islands, 0, 1, 2, 3, 4, 5, 6, 7. You go around the clock as you move along. An 8/3 DTC, which we call fractional here, does it by having 8 islands, but moving through them always in a 3 steps. So it starts to move always 3 steps forward. So after 8 steps, after 8 driving periods, it has completed 3 revolutions. So that's what we call then an 8/3, 8/3 DTC in this problem. Now, of course, there's many things to, this was just basically the main message, but of course you have to check many things. So there's stability to perturbed parameters. So I showed you that it was stable under changes in the driving strength, but you would like to see more, I'm sure. So here is the picture where we see how the state evolves in the whole plane of spin flip strength and interactions. And the story is somewhat similar to what I introduced in the very beginning. So here the point 0.25, which you could call like an integral point, there the response is trivial, if you like, this 4 DTC response. And you see nicely that the interactions stabilize now a full phase, a full connected part of the parameter regimes, which show this type of response. And you can also distinguish, I point out 2 different phases here you can contrast it with, namely a trivial phase and a thermal phase. And in these Gross-Pitaevsky equation, you can also nicely distinguish those two by looking at something called a decorrelator, namely the sensitivity to changes in initial state. So that way you can even resolve differences in trivial and thermal states. So in that sense, there's a whole range of different, it is not a fine-tuned point, but a robust phase where there's a finite region of interaction and spin flip strength where this response is stable. Now I hear you saying, what about all the scaling with system size? Yeah, we look at that as well. So doing the going back from the Gross-Pitaevsky to exact numerics of the double well problem, we did look at what the exact quantum dynamics like in the symmetric sector, of course, as we increase the number of bosons or as we increase the number of spins they're interacting. The response we are talking about here, which is in the GPE equations, becomes more and more stable, as you can see here for the different examples of 3, 4, 5, 6, 7, and 8. So we do think that this response is to infinite times in the LMG in this kind of collective spin limit, of course. You can also see nicely how the different DTCs are converging at a different rate. So if you're looking at the 2 DTC, it converges pretty quickly. Its response converges pretty quickly for a very small number, small system sizes, so at the order of 10. If you're looking at this 4 DTC at these higher orders, then it takes much longer to converge. And this may be a reason why this is much harder to observe numerically by exact diagonalization in more complicated settings. It's now really time to move, away from this collective spin and go beyond the LMG limit. So we are replacing now. We want to ask now the question: what happens if we replace the all-to-all by something more generic, which is going to power law, introduced here, and is characterized by an exponent alpha, or competing with a short-range interaction of strength lambda. So this breaks the full connectivity of the model. If although the LMG can be recovered if we put alpha and lambda to 0. The way we think about this is as we start from the collective limit, and we are treating this as a system which has finite spin wave interactions, and we are of course limiting ourselves to a spin wave approximation where it's just quadratic in the spin waves. So focusing on the 4 DTC, the higher order one we looked at before, what we find is that if we do calculate the spin wave density as a function of time in this approximation, which has been looked at in this paper down here, then we do find, as we vary the exponent alpha, we find 2 different cases. If it's small enough, so close enough to 0, then we find that the spin wave density is non-zero but stays small on the length of time we can look at here numerically. Or if it's bigger, then it starts to grow fast, as I've shown up here. So there seems to be a relatively sharp transition as we, for fixed lambda, move with alpha, increasing alpha. This is shown here in this graph in the plane of alpha and of lambda. This is the point, the LMG point down here. There we think the response is to infinite times, and it starts to be pre-thermal, arguably, as we move away from that point. And there's a transition then to thermal as we move further out. And indeed, if you look at the response at the quarter of the drive frequency, we find a very similar picture. So we believe then that these DTCs I talked about before are survive the presence of power law and even competing short range interactions to a certain degree, and they survive as pre-thermal phases. One thing I have not touched upon so far is perturbing the initial state. I only talked about the fully polarized ferromagnetic state, if you want. In the LMG limit, I implicitly answered it maybe. So namely these islands, which I talked about before in the LMG limit, these are stability islands as well, or you can think about stability islands. So as long as you start inside them, then you're going to see collect the kind of DTC response you've been seeing. The problem is more complicated in the case of beyond LMG. You have more parameters to think about. One thing we did check there is whether this response is stable under injection of spin waves. So we take a system where we now solve these spin wave equations for finite initial noise, and we do find that this is in a certain range stable. So numerically, we can confirm that the response remains very similar, qualitatively the same for finite initial spin wave density. So this is as much as I wanted to say about this bit. I think I'm almost up in time, just to flash out 1 or 2 minutes on the second project about time crystals and bosons. Here we're thinking about n ultra-cold bosons in a ring lattice on L sides, and we're thinking about having 3 stages in the Hamiltonian, hopping between here the red sides from after one drive period, going from here to here to here to here, or for the if you had the initial state on the blue sides, it would move from here to here to here to here. So you have 2 entwined clocks which are moving counter rotating. And the question here is whether this type of trivial response can be stabilized into a DTC. So asking the same questions as before, if you like, what about if I start to move away from the trivial points? Here, can interactions stabilize such a response? And you'll likely say this answer will be affirmative, especially if I throw in the information that this is a bosonic system of n particles on L sides. There is a highly complicated and weird mapping to a complicated all-to-all clock model, similar in reverse to what I've talked before in this kind of Schwinger mapping, and that saves the day that we don't have heating and we have a response of DTC type. Just saying, similar steps as before. We could do exact, but we also do Gauss-Berdievsky type. We're looking at imbalances and decorrelators and find DTC phases. And it again is a full phase starting from a trivial point. Full DTC phase is stabilized in the system. So these kind of counter-rotating clocks can be made into a stable L-half DTC. And what's more, if you throw in a potential term as well, you not only have points where you have a rigid subharmonic response, but you can have rigid subharmonic response together with an additional incommensurate frequency, which is moving about, which we then call a quasi-crystal as incommensurate with the other frequency. And again, there's a trivial point which opens up into a many-body phase as you introduce, in this case, contact interactions. So with that, I'd like to come to a close and just say I talked about these 2 projects here. They have in common that they are clean systems, no disorder needed. There's no MBL to prevent the heat death. Instead, there's the crucial ingredient of long-range interactions here and contact interactions between the bosons here, which map onto all-to-all for a clock model on this side. It's very rich phenomenology with including exotic phases like NDTC, higher order DTCs, and discrete time crystals. In contrast to the MBL DTCs, here we have a semi-classical limit which allows for efficient dynamics, controlled approximations, and we believe contrasting different insights. And nonetheless, these are robust pre-thermal many-body states which are whose robustness is comes from the interactions between the interparticles. So just to close, I said before, this has worked closely with Andrea and Johannes. We've worked on several other projects, which I don't have time to talk about. And I'm looking very much forward to questions and comments. Thank you.
Thank you very much, Andreas. Thank you very much. There is a question from
Sorry, Andreas. Something I didn't get. If I look at the finite state scaling of, say, the decay of the oscillation in the fractional and the integer steps, is it the same or it differs? Is there something
between the fractional and the integers?
Yeah.
Actually, I don't have a slide on that, and I don't know if Andrea has actually how much he checked both. That's the one we have always looked at. Do you suspect there would be?
No, I have no idea. I was curious if there was something qualitatively different or not. That was my question.
I can't remember there was, but I haven't. I don't have a slide, or I don't have the data exactly here, so can't answer that exactly. So Andrea is also, I think, here, and Johannes is also in the chat, so we can look at it again.
Thank you.
Thank you. Okay, so I just wanted to make a short question. So you have all these results that you kind of match with the Gross-Vitaevsky equation, okay, which is a single particle equation. So what is this interplay then between the long range and the short range? Because for me, if you can reproduce with Gross-Vitaevsky, which is a single particle thing, the role of interactions, I don't understand it completely. Okay, so they are hidden in some way, no? In there.
Well, so do you refer to?
In some way, so that all wasn't. Sorry.
Do you refer to the fact that? So you're asking about the many-body character,
yeah.
or?
Mm-hmm. Yes.
That's of course a. It's, I guess with Vedika you saw this morning as well, right? So there's of course many discussions whether about what is a many-body phase and where are many-body effects crucial here. Here it's the fact that if you are thinking about long range, what I said, then it does map onto collective spin, and you are in a regime where Gross-Vitaevsky becomes exact. So that's true as shown here. The interactions, of course, still play a crucial role, obviously, right? As you know, they come into play as the non-linearity of the
yeah, sure.
Of the but it's of course at this effective single particle level. As we move beyond, so I mean, then that's true in this LMG limit. As we move beyond the LMG limit in this part here, this is of course a completely general many-body system, and there you do not in this part here you'd extend explicitly into the full many-body realm if you want, but you're starting perturbatively, of course, in this quite nicely characterized limit where you have collective physics, where you have a nonlinear equation, classical nonlinear equation describing it. We see this as similar, not unlike actually, in equilibrium, the Ising transition, right? So if you're thinking about there, the phase transition of ferromagnetic, then we understand the physics of that transition, but usually by thinking about the mean field limit and studying a nonlinear equation between the magnetization. That's normally what we do, right? And then that does not mean that the transition itself or the states which are beyond are not interesting or not many-body. And there's many other things you can learn about going beyond mean field, but it just gives you a good point, a good starting point to understand the physics in this collective limit, and do a lot of just gain a lot of understanding first before doing heavy numerics and really finding out where transitions are.
Thank you.
So we see it here a little bit similar as in that respect as well.
Okay, I understand. Thank you very much. So,
thank you.
Thanks, Andreas, for this very nice talk. And let's go to the last talk of this morning by Odette Sieberberg, which is going to talk about, I think, classical many-body localization now, not time crystals. So maybe it will be a little bit. Have seen. So thank you, Odette, and everyone.
Can you hear me?
Yes.
Okay, great. So let me just activate my timer that you don't have to reprimand me. And Okay, so thank you everyone. So I'm actually going to talk about many-body time crystals, and I'm going to actually adopt some sort of higher altitude viewpoint on the problem and try to make a little bit of order of how we interpret or understand the different statements that we also heard during the past 2.5 days. In some sense, if you wish, I'm trying to connect to the statement about that you cannot see the forest for the trees. So, and it's probably is related to the discussion that Anna just had with Andreas. And before I start, I would like to first thank Sao and Christoph for inviting me to give the talk here today. I'm actually a condensed matter many-body theorist. We got to look into out of equilibrium responses of many-body. There is like a whole comprehensive list of publications that I would like to bring as context to how we got to look at time translation symmetry breaking. And I would like to, before I go into the details, first thank a years-long theory and experiment collaboration with Chita and our then joint students and Alexander Eichler that performed all of the experiments that will appear along the way. Okay, so we're talking about a many-body system. We would like to actually view the point from a microscopic point of view. And generally, when we solve a many-body system, so from a theoretician's viewpoint, we can exactly diagonalize the system, and then we will have some effective collective mode, or an effective many-body spectrum with associated eigenstates. Generally, this many-body system could be embedded in a larger ensemble of eigenstates that will then appear at very far detuned eigenenergies and will maybe then can be traced out effectively as some sort of dissipation. And into this midst, we want to now add time-dependent drive that you can also additionally think about as some very massive additional degree of freedom that just moves with its eigenfrequency and shakes the system in time. So as context to what developed our higher altitude viewpoint was that we actually wanted to look at this generic light matter model, the Dickey model. So in 2014, we are, as many-body physicists, we said, hey, what happens when we start to take many spins and couple them to an optical cavity? This model was already proposed by Dickey in the 50s and was then solved by Hepp to show that there is actually a critical symmetry, Z2 symmetry break, Z2 second order phase transition, sorry, got stuck there. And technically, this model got a new bliss because it can be realized in out of equilibrium systems, so in the rotating picture of light impinging on cold atoms trapped in an optical cavity. So with this, I refer also to the talks by Andreas Emmerich and Angelo and Jamil. So we looked into it, and effectively, what you can do, and this model also then relates very strongly to the spin models that we saw during this conference. You can actually make some generalized mean field description of the problem, and you can then solve the problem and get this critical phase transition. But on top of it, you can also decide to study the problem as to adding a time-dependent interaction between the light and the spins. And that tells you that you're actually now shaking effectively the spins collectively. And this can then be realized, as we also proposed again in this work, by a time-dependent shaking of the intensity of the light, as was then later realized in the Hamburg experiments. So effectively, we were at that point in time technologically making our first steps into such an environment. So we did add a little bit of dissipation, but most of the statements I'm going to say are actually not arising due to dissipation, and this I will elucidate in a couple of minutes. So let's start. We first solve our mean field equation, so I didn't write them here explicitly, and we can write ourselves relative to positioning ourselves into the superradiant phase of the system and then applying such time-dependent drive. And then you see that technically you will obtain something that looks like superradiance. I will show to you in a second what that now means. And on top of it, you can also go to other regimes where the whole light field is oscillating wildly. But what is important for the conference topic is that when you Fourier transform these time oscillations, you also then start to see response of the system in subharmonic resonances with additional sub-peaks that are then incommensurate with any of the drives and are generated due to the interplay between the time-dependent drive and the nonlinearity imposed by the spin conservation of the problem. Looking at such time traces and taking their time average, you can then draw a mean field phase diagram where what you can see over here is the ratio between the frequencies of this parametric drive and the amplitude of the parametric drive. And what you can then obtain that there is actually a frequency that here, when the amplitude of the parametric drive is 0, you can actually see that here we see the standard Dickey phase transition, the superradiant phase transition. But as we increase the drive, the superradiance continues, but starts to develop all sorts of funny looking mean field observables when you look at the spin, generalized spin projection along the Z direction. So we looked into it further, and then also, by the way, here on the second panels, you can actually see how many then subharmonic and additional harmonics you start to generate as you drive there. So here is a count. Sorry, here is the amplitude, and you can also count how many of them are being generated. Looking more closely and seeing what the spin actually does as a function of time, you can actually see that due to the coupling between light and matter, the collective spin starts to tilt away from its quantization axis over here. And then due to the time-dependent drive, it starts to precess, and it will perform limit cycles with many different frequencies on the Bloch sphere. Generally, when you're analyzing such models, you can also then see the stability of your mean field ansatz by performing a fluctuation analysis of such a model. And at that time, we just looked at the stability analysis around the normal phase, namely when the interaction is negligible. So we wrote down the Holstein-Primakov transformation of this creature. Generally, it looks like this. When you expand around the normal phase, the empty cavity and all the spins pointing down, you start to see that you have two effective fluctuation modes that have a time-dependent coupling between them. And with this, by the way, I would like to also refer to the talk by Jamil, where he actually did a similar analysis, but also around the limit cycles of precession. But this was a more sophisticated analysis that was performed later on. So generally, when you analyze the stability then of these two coupled, time-dependently coupled harmonic oscillators that arise from the fluctuations here of the light and matter, you can actually form two normal modes of these creatures. And what we find is that you have actually two parametric resonator normal modes that each of them can become stable or unstable at different situations. And that actually tells you that our whole treatment of a mean field plus small fluctuation is only relevant where we have the overlap of the dark blue regions of both fluctuation oscillations. And this is then these zebra lines highlighted over here and corresponds very well with the mean field treatment as you see over there. So by combining these two, we actually then predicted the emergence of a dynamical medi-body normal phase, which would have then stroboscopic light bursts as the matter starts to precess in the time-dependent drive of the system. So having done this analysis, we actually then realized that we feel very uncomfortable with invoking all of this parametric oscillator know-how because we didn't feel like we understand sufficiently the individual resonator level, okay? So we got all the way back to the beginning and we looked at a simple linear parametrically driven oscillator, and that was already elucidated in this conference. Depending on the time drive of this parametric time drive, you could have instabilities. regions where the oscillator completely decouples and does not respond to the drive, and regions where the drive enacts a resonance, but this is not a standard resonant response to an external drive. It's a resonance that is going under the name of parametric resonance, where actually you could have different conditions on the ratio between the bare frequency and the parametric drive, and it will occur for even infinitesimal driving of this type. We should all feel very comfortable with such an effect. This is exactly what happens when we stand on a swing and we shake it. So we actually, at twice per circle, per round trip of the swing, we kick it twice with our body motion. It's important to notice that this stability analysis is at zero dissipation. So dissipation does not play a role here in these instabilities. And it's also then important to notice that if we want to go and understand what will happen over here, the linear oscillator is then not enough to understand what's going on, because for the linear oscillator, all motion should go to infinity, and we know that in a real system, this cannot occur. You could analyze it in the classical domain or in the quantum domain. So here, just for completeness, I showed to you that if we take a quantization of such an equation and we also add, say, cubic nonlinearities to the problem, you can quantize the fields and it would look effectively like an optical cavity or a quantum resonator that is driven by a 2-photon drive. And here specifically, I write the Hamiltonian already in the rotating picture with respect to half the frequency of the drive. So here you can already see that by moving to the rotating wave approximation, you see the time translation symmetry breaking occur as a standard Z2 symmetry of the model. So we are still here at the zero dissipation, and we can really even draw the Landau-Ginzburg potential landscapes for such a nonlinear oscillator, and you can really see the Z2 symmetry breaking. And as we are in a rotating wave approximation, this will occur due to the interplay between the 2-photon drive and the nonlinearity. So it's not because we have a dissipative system. This physics, these period doubling bifurcations, they occur at the interplay between these drives and nonlinearity. What does dissipation do? So, I mean, there was this distinction of mean field versus dissipation versus many body. So effectively, until now, from what we have seen, we take a many body system. It forms a collective mode, an effective collective mode. In our Dickey model, it was actually 2 coupled effective modes that were coupled to one another. And the period doubling instabilities, they seem to occur also for a single mode. So effectively, we have to kind of divide and conquer. Does the period doubling bifurcation occur because it's many body? And what is kind of the game that we're trying to play here with? So what I called the title of my talk, Classical Many Body Time Crystals, but in fact, you see that the period doubling bifurcation here is really not due to dissipation, it's due to nonlinearities. Adding dissipation, what does dissipation actually do in this context? You can think that the resonator effectively weakly couples to a bath that has some noise statistics associated to the frequency distribution of all of the other modes that this mode has coupled to. And if you then analyze the stability of this creature, it will actually push the phase diagram's boundaries away from infinitesimal time-dependent drive, but it will not stabilize. It will not stabilize because the drive is a 2-photon drive, and it kicks an exponential amount of energy into the system that cannot be stabilized by standard dissipation. Okay, this is a ubiquitous effect. In fact, many applications occur here in this stabilized region, where the parametric drive acts as effective nonlinear damping, and then the motion of the oscillator subject to either thermal or quantum noise will be then squeezed, and you can then use it for amplification applications. moving beyond the threshold, the system will undergo this time translation symmetry breaking now in the presence of dissipation, but we are aware that it's no longer because the dissipation is stabilizing it. And the system effectively will now if we look at it, so here is the phase space distribution of an experiment measuring how the system then likes to appear at this type of histograms that we saw so on the first day of the conference. But of course, if you don't measure it with a lock-in amplifier, you will see that the system undergoes this time translation symmetry breaking, and the excitation will get back to itself after 2 cycles of the system. I referred everyone to these 2 works over here, and this would be probably a nice context for people studying these effects in different resonators. So now the top view approach, we set out in the beginning, actually, we were intrigued by these effects, and we were intrigued by nonlinear physics involved in this. And then we set out to look at actually the interplay between 2 different drives, the parametric drive and the external drive. But first, I would like to show to you what happens when you just isolate a single collective modes of an Avogadro number of atoms forming a half a meter long guitar string. And you can actually then drive the string externally, or you can drive it parametrically like we saw in the equation of motion before. And this is done by pulling and unpulling over time over the effective tension that this material problem entails. The effective equation of motion describing the system looks like this, where the stretching and non-stretching enters as this Matthew time-dependent drive over here. And we have effective nonlinearities occurring due to the bending, higher order bending moments of this beam. This can be done on also essentially also on a carbon nanotube, but this effective equation will be the same there as well. We scan now the drive, the parametric drive over this highest instability mode. And then indeed what you can see is this characteristic hysteresis cycles, where here effectively the system undergoes a Z2 symmetry breaking to the time translation symmetry broken state, and then obtains 1 high amplitude that would be that the system sits in one of these phase states. And of course, if you scan down, you will see here a jump up, and this allows you to then trace out the boundaries of this phase diagram. You can also solve the steady state analysis of this creature, and you can really obtain all of these stationary attractors in the rotating picture and mark all of the places where bifurcations occur. Technically, we are now interested in this thermalization and studying what will happen, or how long-lived with this will this type of oscillation persist. So effectively, before the realization was in the collective mode of a half a meter long guitar string, you can also take an RLC electrical circuit that obeys exactly the same equation of motion as I showed here. And then you can drive it also with noise. So if you don't drive it with noise, the system is effectively coupled to a 0 temperature bath. And you would see that the system undergoes its time translation symmetry breaking and effectively locks on to the parametric drive and stays there forever. If you increase the noise, what you see is that you will start to get this telegraph noise. The system starts to explore weak noise around its attractor and then gets activated to move to the other time. The characteristic activation rate over here is what is going to actually kill your time crystalline phase, as it starts to then, by being subject to coupling to the other modes in its environment, and that then activates it to get a phase slip. If you take such time traces and put them in phase space, the probability distribution function domain, you really see that in the end, the system regains ergodicity and explores both time translation symmetry breaking attractors. And technically, if you want, you can go more microscopic into it, and then you can see that when you focus at weak noise activation, you can Fourier transform such motion, you can compare it to the spectral function response that you expect for the system. And by this, you can also then extract from the frequency at which the system responds to the noise and the width, you can extract all of the Lyapunov exponents or Liouvillean eigenvalues that are associated to fluctuations around these time crystalline states. So with this, we saw actually in the conference that people kind of try to you know, get at this problem and review it, and there were several references at the history of first experimental realizations versus not. I would argue that technically, if we go all the way back to Faraday, when he took all of his particles in his water glass, they formed together a collective mode that then, after the shaking of his hand like this, formed again those mode that responded most strongly to the parametric drive and showed parametric resonance or time translation symmetry breaking. Riley already wrote an equation of motion similar to what I have described for this effective mode that appears, and this leads to then Matthew type solutions to the problem. This field has seen many realizations that actually every person that more or less looked at this problem wrote a patent, and there are various applications for parametric resonances, either for sensing or by actually encoding information in this phase information of the system. It actually has even applications for waves of water driving oscillation motion of a rigid body, and it has huge applications that even an infinitesimal drive can make this to boats, or if it couples to another mode of the system, it can do that to it. So all in all, we even teach a course on it. This parametric resonance manifests in more or less all fields of physics. It's ubiquitous. And if I kind of want to go back to look at the forests, I would say that what we're trying to do in this conference and now in this community is to try to engineer through the many body the different collective modes. And then by seeing the many-body physics, see which collective modes respond to which drives, under what effective nonlinear coupling to other modes, and what other effective dissipation channels that exist. Of course, depending on the many-body microscopic system, we would see that maybe Lindblad is no longer a good enough description of the problem. But all in all, I wanted to use this talk in order to kind of make a divide and conquer. That I would say the time translation symmetry breaking is of the parametric resonance type. In optics, people call it second harmonic down conversion. So it appears in a variety of fields. And as a society here in the time crystalline domain, we need to stop and say, okay, what are we trying to then obtain with our many-body realization? And for this, here I wanted to also highlight this experiment that Mark Dickman and collaborators from Korea showed, where they took many atoms and shook them in time. And then they also underwent this time translation symmetry breaking. But then I asked, what is different than this type of experiment and the guitar, half-a-meter long guitar string? And this is in the 1 minute that I have. So this is kind of to show to you that even in Bell Labs in the 50s and 60s, people already found applications for such parametric instabilities. And in the same way that this was a pioneering commercial from Bell Labs, I think that we are at the era that we need to go beyond this single collective mode and see where we can go. So where can we go? I use another 2 minutes, Anna, sorry. we can see whether our equation is really susceptible to binary drives or cosine drives. And this is not the case. Actually, this is going under the name of Meissner driving in the older literature. And the only instabilities and where they occur appear and manifest only at the commensuration of your Floquet driving cell and the eigenfrequency of your collective modes. So this is what happens to the stability Arnold tongues as you add dissipation. You could add more drives, and actually you can break the time translation symmetry breaking as a function of detuning, and this can give you additional fun hysteretic controls on how you can switch between which phase of your time crystal you fell into, and this we could also apply in this 0.5 meter long realization, where actually it matches very well with what happens when the child wants to swing its swing and the parent tries to interfere in the middle. So hence the picture over here. You can try to go quantum, and you realize that all of these macroscopic, it's called gas to liquid phase transition. It's of first order type here, from a low amplitude in your resonator to high amplitude in your resonator. If you add quantum fluctuations, it will make all of these first order transitions into crossovers, including the one that we then showed with the phase symmetry breaking over here, and as well as the Z2 transitions. All of this, if you go deep nonlinear, is closely related or identical, in fact, to the recent realizations in Devore's group in Yale of cat qubits in driven RLC resonators. So if you go deep quantum on this mode, you will get an effective few photon qubit with a parity even odd realization of this system that seems to be very robust to noise, because on its Bloch sphere there are two coherent state embedding in the encoding. If we go into using these phase states for logic, actually the first Japanese computers were using RLC circuits and encoding bits in these two phase states. We then went and looked at how we can activate and manipulate these type of states as activation and fast activation for actual application of using these time translation broken states for encoding logic. And then technically, if you go beyond and you would couple many of these guys, you will now be able to generate annealers and simulators that can be either classical or quantum in the NISC notion thereof. So I'm using Star Trek's Discovery again to say that if we want to go many-body, we need to have many of these guys. And specifically, we need to actually have that the system has many collective modes, that each collective mode undergoes this time translation symmetry breaking and interacts with one another. And effectively, you can really think of it that if we have these Arnold tongues, now if we have many modes, they will hybridize together, they will form new normal modes, each will have its own instability lobe associated to it, and we probably need to go to this region over here. I finished, sorry. We actually went to explore it. Truly, you could have strongly connected modes, and then they would form new normal modes that would act in their own as a single collective mode, even though there are now more of them together. But if you have weak coupling and these instability lobes overlap, this is where more stuff occurs. You have 25 attractors to the problem, and many, many things can manifest here. We went to explore the many-body physics also with noise, and here you also see bifurcations that lead to metastable states. We call them ghosts because they actually participate in the noise activation in the system, and this is actually something very interesting for the manifestation of all of this as Ising simulators. So with this, I want to summarize that I claim that the microscopic leads to effective collective modes that have nonlinear coupling to their environment. The microscopic is extremely interesting in order to then find out whether we have isolated modes or not. Nonlinear resonators show period doubling bifurcations, and then we can ask ourselves, do we have a many-body period doubling, where many modes undergo this translation and then interface with one another, or do we have a single one that does that? The role of dissipation is marginal and only pushes the threshold away. And technically, if you do couple more of these, new things occur. So with that, I would like to thank you for your attention.
Thank you for that. Your watch is not so precise, as you said. But anyway.
Sorry.
So I have a question which has very little to do with your talk. May I?
Yeah, sure.
Okay, so I was wondering when I was listening between the difference between this classical, so you argue that this classical oscillators, if you want, or driven oscillators, okay, display all this physics, which I completely agree, or these discrete time crystals, if you want. And I was wondering something holding this conference, right? And you are a body physicist, so maybe you will know. I was thinking that the big difference between classical and quantum, in case that they exist, is that one should be able to see a kind of violation of Bell inequalities on times, whatever it's called, legged inequalities. Okay, I know it's not very related to your talk, but this is what it came to my mind. So I wanted to ask you this, and exactly another thing which is also related. So you were saying that these parametric driven systems have been using for metrology, okay? And then I was wondering which science sounds pretty reasonable. So should that be the same if you are quantum, and instead of having that measure and then feedback and so on, just having a time crystal which can be used for quantum metrology?
Okay, so you asked two questions that I will try to answer as two different ones. Technically, if you start to look at these out of equilibrium systems, or you try to even derive a Lindbladian description of what's going on, then we get very fast to also what Ueda told us yesterday, that we have actually something that will be jump kicks from the fluctuations that hit our system, as well as something that gives it a lifetime. Okay, the classical systems that I showed to you, so for example, a 0.5 meter long guitar string, if you drive it in the way we drove it, it's never going to decay. It doesn't talk to anything else in the universe, more or less. Okay, yeah. So effectively it talks to a zero thermal bath, right? Yeah. If you make this smaller and smaller, your quantum fluctuations will activate transitions between the two low photon number minima of your system. Okay, and that would probably be what happens there, right? I mean, this would lead to these crossovers that I showed over here. I'm going to try to scroll in parallel, right? So if you look over here, so actually everything becomes a crossover at a certain point, because inherently you have quantum jumps that then make it that it's hard for you to distinguish at which bifurcated minima of your Hamiltonian you're sitting at, because the nonlinearity is so strong, the number of photons is so small relative to this Z2 symmetry breaking, and then the quantum fluctuations will make you hop extremely much. So this would be what I would say is a direct manifestation of what quantum will do. And therefore you will have very short lifetime for your phase states to exist. Now, relative to entanglement and Bell inequality, entanglement is always a question of relative to what, right? So, I mean, even when you drive the system and it's squeezed, and you would look at the photons so vacuum photons in this squeezed parametric single oscillator, then you squeezed quantum fluctuations under the parametric drive, and then you will have actually a higher coincidence. You see quantum already over there. Okay, and now if you want to look into your many-body system, then it depends. It could easily be that you squeeze the collective mode in your many-body system, and now you want to, in space, see how two spins are connected, then you will have entanglement.
I want to see it on time, but anyway, not in space, but anyway. Saro wanted to ask something.
Yeah,
so
just a quick question. In the telegraph noise that you show, the rate of the transition rates from one side to the other is just thermal, or there is something more because of the...
So this is a very good question. We in the experiment we're deep classical, so to say. So I mean, I think on the first day of the conference we have 10 to the 8 quanta, if you wish, and therefore we have to induce noise externally. So and then this is thermal noise, and we use white noise. For activation barrier questions, colored noise is then becoming very interesting. The rate of activation is intimately close to what people call Kramer's turnover. But actually here it will not be Kramer's turnover, because dissipation has a different role than in standard potentials of the system, because we're in a rotating frame. So this is something actually interesting to look into. There is, in these parametric resonators, there's a work by Mark Dickman where he is showing that these systems have effectively to their activation rates an additional contribution that he denotes as quantum creep. So there will be an additional quasi-quantum effect appearing here as well. So yes, it's very interesting.
Okay. So if there is no more questions, Zaro, you want to close the session?
Yeah, just I would like to thank everybody, and thank you, Anna. So thank you, Oded, and all the speakers. I think we can get a break and resume at 2 p.m. Central European time. Okay, see you later.
Bye.
Bye, thank you.
Professor Liu, can you hear me? Are you connected? Professor Liu? Professor Kozier, can you hear me? Okay, thank you, Professor Kozier. Would you like to check your presentation to share your screen for the lecture that you will have today? Yes, I've seen you're muted, but yeah, you can, okay. Okay, I can see your slide in presentation mode. It's okay. Thank you. Professor Liu, can you hear me? You're muted.
Now it's unmuted. Yeah, great. Just
Okay.
wanted to say hi to
Would you like to check your presentation?
yes, let me share the screen.
Yes, thank you.
Let's see. Thanks so much.
Welcome.
Can you see that?
Yes, and now, yes, perfectly. Presentation mode is full screen. Perfect.
Great. Thanks so much for everybody.
Thank you.
Greetings to Sasha and Professor
Thank you.
Fazil. Yeah. So Sasha, how do I pronounce your first name? Christoph. Is that correct?
It's fine. It's fine.
Yeah.
Yes.
So
Yes.
I try to learn how to the best way to call your name in the correct way. Thanks so much. See you guys soon.
Yeah.
Let's see.
So all the three speakers tested the connection.
I don't know if Al Shapere did test the connection.
Okay.
But I don't know.
Because I just joined.
Oh, yeah, he is.
Okay.
Maybe.
Okay. I'll mute. Okay. So you have. So did you, Alshu, did you check? Good morning. Hi. Did you check your? Did you test the presentation already, or?
What's that?
Did you test the?
No, I'm here to test.
Okay, so I think we can try now.
Okay, just a moment. I'm sorry, do I need to be a, oh, I see, share screen, I've got it.
Yeah, I think it works fine.
Okay.
Sorry, because they always ask this. Do you have videos or in your presentation or just slides?
No videos.
Okay, so that's perfect. Thank you.
Okay. And if I show it this way, are you seeing the full PowerPoint page with the or is it in presentation mode? I can't really tell.
Yeah,
Now it is.
Now it's presentation mode. Now it's okay.
Okay, good. And let me just also check the, can you see my mouse here if I do this?
Yes.
You can see my mouse. Okay.
Yes.
Good. Okay. Then I think we're set.
Yes. Okay.
Yes.
Thanks a lot.
Okay.
So I think we have 10 minutes. So.
Yes, sure. We started on time, so that's.
So far at the end, it worked very well also with timing and things. I was a bit worried this morning, but what happened was that Multisegev was registered under a different name because I think he connected from the phone or something else. So that's why we were not finding him in the list of participants. But
yes, I think that because he said that he lost his email and connected via Victoria, let's say, account.
Okay. Okay, that was the reason. Okay, so you know more than I do.
No, I got it. I don't know.
Okay, good.
But finally, it was okay.
Yeah, it was okay.
Okay.
Good. So I will just disconnect for a few minutes and then connect it to.
Sure.
Okay.
See
you later.
I am okay. Yeah.
All right, so maybe I'll start share.
Sure.
Thanks so much.
Mm-hmm.
Let's see.
Okay.
So it's warmer. I'm in Pittsburgh. I guess it's pretty warm in Italy, right?
Well, actually, not really. In Trieste, it's cold.
In the most
or at
part,
least, yeah.
not
So
yet.
I think at
Okay.
the moment, I mean, we are around in the morning 1, 2 degrees above zero.
Oh, that's okay. A
3,
little bit
4,
surprised.
something.
Yeah, that's like we're here. So,
Okay.
so I still had a fond memory of visiting Trieste. Hopefully, we can have that opportunity in the future soon.
I hope so. I mean,
so currently you guys are still running program. That's wonderful. So are all the programs online, or you still?
Yeah. So I think, and as far as I can say, yeah, until August for sure, August, September, and then we are evaluating if situation changes.
Yeah.
But it's complicated because all the people that come from outside have to go on quarantine. So it's, I mean, having conferences is very difficult for many different reasons.
So I think we can start. So welcome everybody at the last session of the conference. And the first speaker is Vincent Liu from University of Pittsburgh. So Vincent, the screen is yours.
Thanks so much. I want to start by thanking the organizers, especially Professor Sasha and Professor Fazil for inviting me to this very interesting conference on a special topic, which is very timely. Also, I had this opportunity to know many new friends on the screen, to learn new physics, and also meet old friends like El Shapere, who is coming up next, who have not seen for quite a while due to pandemic. Okay. Anyway, today I'll talk about, I would say I'll report 2 results. One is actually on the Floquet time crystal without the disorder. I want to spend a few minutes on that. And then the second one is to propose a new idea on imaginary time crystal. And this work is, this talk is based on work in collaboration with following people, especially my postdoc and collaborator in Shanghai, like I think he's in the audience. And so I decided not to give any introduction. I think many speakers in this conference ahead of me already did a great job. Also, Frank Cloken, I understand from the test slides shown by El Shapere, he will actually give more, background regarding the origin of time crystals. So I'm gonna just go straight to the results we worked in the last couple of years. So first I will talk about the clean time crystal. Then the second part I will talk about imaginary time crystal, and the macroscopic level, a temperature crystal. So part 1, we come into this question by asking the following question: is the concept of disorder or many-body localization really necessary for the time crystal? Let me try to minimize the side view. Let's see, somehow. Guess I can do that.
I think it is fine.
It's fine? Okay.
Yes.
Okay. That's good. All right, so let me get my laser point back. All right, so then we seem to have found a model that indicates that you don't really need this. So let me get to that point. I just want to make a quick introduction to pave the way for me to introduce the model we're working on. So think about it today, it's like in 2018 or earlier. At that time, people already think about how to get around with no-go theory, and there are many great ideas by introducing the district/Floquet time crystal. That means go beyond the logo theorem, by go beyond the assumption of the logo theorem. All those models, as far as I know, those pioneer work by those people, the models proposed by those pioneer people, seem to indicate the many-body localization is a key element to stabilize the so-called pre-thermal time crystal phase. Then shortly after that, the experiments in Maryland and Harvard confirmed those predictions. Very remarkably, I just want to point out that in the early experiment by Maryland, they found indeed this disorder is essential. However, in the Harvard experiment, as everybody knew so far, they have performed both cases with or without disorder. Very recently, actually this year, the Maryland group had actually, together with Norman Yao and others, collaborate in theory, also did the case without disorder. I will not talk about that update. So what is the particular model I want to actually introduce? So the idea is actually based on the periodic driving. So you have a given period like a T. Unlike the other models before us, we do not have a disorder. That means we can only have 2 time intervals in one period. So in the first period, T1, it's a kind of like a Rabi oscillator. So here we have a model based on the atoms. The previous models are based on the localized spins. So we try to do like Hartle bosons or fermions with the idea of cold atoms. Later on, I will talk about the realization, how to use cold atoms to realize this model. So this is like Hartle bosons. There's a hidden term associated with the Hartle condition, which is not shown. You can also think about it as called fermions. So the first term is actually just switch between the leg A and leg B. Think about it, you have is a ladder with 2 legs. You populate 2 legs. However, this one actually would change this population imbalance, I would say, between A and the B. So for that, we define something like a pseudo-spin polarization. In the sense, it's the difference between the particle number between A chain, leg A and leg B in the ladder model. In the time interval 2, this is actually is a condition, very typical along the chain tunneling, hopping. Then we also have this near-label interaction. On top of that, there's a constant delta here. This is not disorder. So it's just like a energy imbalance, which will be present in the model. It's not so important in our model, by the way. And let me just get the results. So we have done, especially my collaborator, my postdoc actually, I've done this exact diagonalization and also by the DMRG, and both actually indicate you could have 2 phases. This is the case without disorder, by the way. We never had any disorder in this model. That's our goal, to test whether it's possible to have time crystal phase. As you can see that when the interaction is strong enough, this is strong interaction case, this is the weak interaction. And indeed, the period of the kind of like time crystal phase is locked to 2 pi. So in the frequency space, the spectral weight function peaks at pi in this axis of omega. That actually indicates the time crystal satisfy all the criteria people introduced, like rigidity, persistence, all those conditions satisfied without disorder. When the interaction is weak, we did find that the perturbation away from the perimeter in Hamiltonian, you're actually gonna see this, the period is gonna going away from 2 pi. That's not a time crystal phase. There are some other results. I given the time because I want to focus more in the second part. So I'm not talking about the detail. In the later on, I think in the 2018, there was a paper by Yale group. They also started a system with spatial ordered crystal where they also find a time crystal. And in our system, there's no disorder. So that result also seems to be consistent with the statement that the many body localization may not be so necessary for the time crystal phase. Then in the last few slides for this first part, I'm going to ask a question: how do we realize in the cold atoms other than the localized spin models like trapped ions, system of n-way centers? So here, let me just propose one model, and in the paper we actually talk about other ideas. So let me just talk one of them, just be focused. That is actually we're gonna, it's possible to use, say, the dipolar gases to test this idea. So let me just tell you a little bit. So this is the TAI model, and this side is more like a step 2, from TAI model to the realistic model, and step 3 will be someone go ahead and do the experiments. That's a typical roadmap from an idea to the observation. And talking about the realistic model, I think it's possible to use use optical lattices to form a ladder. And the thing about the y direction is double wheel, and along the x is like one-dimensional lattice. This is rather versatile because you can change the lattice constants in space in y much greater than x. So that means kind of like it is not much interaction along the between the chain. You have interaction along the chain. That's exactly what we need right here. And then you wonder why you want to have dipole gas, especially you think about the polar molecules. For those audience, I guess look at the list of participants. Many of you may not so familiar with cold atoms. Some of them are very familiar. So let me just make a few remarks. That is, for the polar molecules, without the presence of electric field, the dipole moments are 0. So in the presence of E field, you can induce the dipole moments. In that sense, you can induce Diaz-Label interaction. So in this model, we need Diaz-Label interaction, but the dipole interaction with a little longer range will do that. So by turning on and off the electric field, you can turning on off the Hamiltonian, basically the interaction term. That means you can go into T2 or you can stay in T1. So that's actually the way to drive the Hamiltonian steps. And that actually is the phase diagram associated with that. So anyway, so the take-home message for this part is you don't need, it seems to me, there's a particular model that shows you don't need many body localization idea to stabilize the time crystal. And also the long-range interaction is not really a key in this problem. This is just a Diaz-Label interaction here. And the possible ideas actually can be tested in for example, in the dipolar gases. All right, so let me move on to the second part in the next 15 minutes or so. Maybe about that's time frame. So I think it's 25 minutes, right, in total. So second part is actually a little bit more on the TAI model level. This is actually in close cooperation with Zitai. So we are asking the following question: what is the thermodynamical analog of the time crystal? In the original paper by Frank, one of his paper, I think, he actually pointed out the possible idea of imaginary time crystal. So here we are even trying to generalize to the thermodynamical open quantum system. That is actually an idea. So let me first give you a few slides to heuristically introduce the idea to argue why a imaginary time crystal is inevitable by the physics we learned in the statistical field theory. So let me start by asking the following question. Typically, when you think about the temperature dependence of observables, you might get into one of the top 3 situations. For example, you could have a observable such as resistivity in the metal that grow that should grow as monotonically as function of temperature. Or you could have something go down monotonically in temperature, like 1 over T, for example, like a spin sensibility according to Fourier-Weiss law. Or you could have a situation that show a peak, such as heat capacity in the superfluid phase transition. So that indicates something like phase transition. Yes. Then you wonder, this actually never happened in the history in the past, but you wonder whether it's possible to have a observable, it's not a monotonic, but oscillating with some kind of period in temperature. This is temperature, not time. So that was actually the kind of like the idea, and that actually also relates to Frank's imaginary time crystal proposal. If you comment in his paper near the end of this conclusion part, I think in one of the papers. The reason is comes to the following slide. That is actually we understood pretty well. For example, in the zero temperature, a d-dimensional quantum matter is actually equivalently mapped to a d+1 dimensional classical matter. The famous example is the, like a 2D Eisen model, classical Eisen model, is mapped to a 1D quantum transverse field Eisen model. And those results, it's well known. At a finite temperature, for a d-dimensional quantum thermal matter, like a quantum sample, the partition function can be written in two equivalent forms, as we know from this statistical mechanics and the statistical field theory. It could be described by Hamiltonian in the deep dimension, or by using the path integral, you can describe that by d+1 dimensional Lagrangian. You just go into the Euclidean space, and by introducing the so-called imaginary time axis. So that is actually the idea. And the time limit is actually the inverse temperature, beta, right? So that was actually a well-known result. So having reminded all of us that, that the dual theory between d+1 and d, then you come back to here. Suppose I'm in the d+1 dimension, say x, y, z. You already discovered some many body states that breaks, translational symmetry in the spatial axis z. Suppose, for example, you can have a charge density wave. We have many examples in solid state materials like that, and they were also in other soft condensed matter systems as well. Then you think, okay, here, by doing the mapping from the knowledge we learned in the statistical field theory, you say, okay, we should have something along the two axis, which is imaginary. We should have something like a spontaneous symmetry breaking as well. It's just like from Lagrangian, to this Euclidean Lagrangian, right? So it's kind of like very equivalent mathematically. So that was the idea. So if you buy the idea, you could have a spatial crystal structure that breaks the translational symmetry in Z. Then you should have something that breaks the translational symmetry in two. So that was the idea. So I think it's pretty convincing. So the next is try to figure out a particular model to prove that it kind of like a heuristic argument. That will be in the next few minutes. I'm going to convince everybody with a particular model. So that actually will be my remaining job. So far it's the very generic idea. I think it's pretty robust on that regard. So what is the model? Here we are trying to think about that. There's a no-go theorem for the time crystal, as we know that pretty well by now. Then that means the problem has to be time dependent. Should it be beyond like Hamiltonian problem, right? So if you have Hamiltonian, you think about it, there will be a term that time dependent. So here's our idea. We're going to consider a time-dependent interaction. So the time dependence enters the problem through the interaction, not through the potential or through periodic driving, not through the single particle term. That's actually the main point. And such a interaction, kind of like in Lamarckovian, for those people actually talking about in the last few days, in various systems, you could think about this interaction, could it be, kind of like effective interaction, could it be generated by coupling the system to the environment? You could have a atomic system coupled to a photons, and you could also encode that as you're talking about the boson-Fermi mixture, etc. And so this kind of interaction term could happen, and we don't have the particular model yet. That will be a more realistic down the road. So far, it's like a toy model. So what is the main feature we would require from the study we made? So number one, so this potential, this is the interaction potential, it's function tool. By the way, I assume the V is local, it's like delta function in the position space. So I suppress the spatial indices for the moment, just focus on the time indices. So it's, we actually require from the model we studied, this potential should have a minima at a certain time scale. And that time scale actually will set a kind of like a lattice constant in time axis in the future. And this oscillation is not very necessary from the model we studied. We studied class models, but otherwise, to be more concrete, we take this particular form, which has some kind of oscillation and also some long distance decay. Second point I want to mention is that we have time-dependent problem, but we do not violate the translational symmetry because the time dependence is through the relative time. So that's actually the key. Then this is the particular model. It's a model in 1+1 dimension. It's a hardcore boson system. It's a lattice in the X, in the spatial dimension. Otherwise, it's a continuum in the time space, in the imaginary time space. So it's 1+1 dimension problem. And for this particular problem, we actually use this interaction, time-dependent interaction term described by this coupling strength, alpha. So alpha indicates how strong this new term, this new time-dependent term is. And in this 1+1 dimension problem, especially when we deal with hardcore bosons, my collaborator was very able to solve that by quantum Monte Carlo simulation. Let me just highlight a few key results given the time. We actually calculated, for example, the density correlation function as defined here as function of time and space. And here, this one shows, for the moment, we're going to focus on the case time dependence, the imaginary time dependence. That means we're on the same site, same lattice site, but different time for the moment for this correlation. Then you did find there are two situations, two cases, I would say two phases. And like the black lines, red lines, they're weak interaction, alpha is low. And then for the blue and the purple, as you see, alpha is greater than like 0.2 and higher. Then you see there's a kind of like two different phases. For the strong interaction, you see a periodic oscillation. This is time axis, imaginary time. And you have some kind of like a emerging time scale come out of that. So it seems to indicate, evidence to indicate that it's a spontaneous translational symmetry breaking, and it indicates a true long range order by this case. This is actually somehow seems to be a true long range order associated with this symmetry breaking. And I'll come back to that moment. It's actually, it's continuing in the time, but it's actually district in the X, so it's a joint continuum plus continuous symmetry, plus it's a continuous symmetry plus district symmetry. So we'll talk about, if you're interested in talking about, whether it's possible you have a break the continuous symmetry. So what do we break? I think is really still a partially district. Then you can actually extract this something like an order parameter by projecting this correlation function in time space on a particular Fourier component. And you realize again that will confirm two phases. And by the way, this is the thermodynamic limit. As you can see, the horizontal axis is the inverse of the length of the system, the lattice size in the X dimension. So the zero means you are in this 1/L goes to infinity. As you can see, when the interaction is strong enough, that's like those two cases, like blue case and the green, and the order parameter, those numbers are finite. And for other cases, like weak interaction, you see the order parameter for time crystal is 0. And also in the spatial part, like the structure factor in the spatial sense, according like S of R, it also has a finite MS, and this is the in Tor space. So M sub Tor, and MS is also finite. So it's actually a space-time locked crystal phase. And then you may wonder the origin. Actually, I already mentioned a little bit in the spatial crystal, you require a minima in the interaction potential. Here, we kind of like require a minima for the time-dependent potential. That's actually the origin. Then you can also, well, because, you know, talking about the Hadamard bosons, you also think about in the 1D, you have this quadrant long-range order that may be superfluid, right? So we calculate the Green's function as defined here. It actually does show that actually has algebraic decay, a strong indication you have this one-dimensional, quasi-one-dimensional superfluid order exists. Very surprising. However, when we calculate the compressibility, it actually shows finite. This is the case above a critical value. This is above critical value in the sense you are in the time crystal phase. The kappa is finite in the sense you have energy gap. So it's like a superfluid versus a gap. So it's kind of like very, you know, intriguing, not very conventional. So this is the phase diagram. You have time crystal phase when the interaction strength alpha is greater than alpha C. And however, it's actually a Landau liquid, which is very normal when the time-dependent interaction is weak. So we recover the well-known result at the low interaction strength. And that's actually a Landau liquid with one gapless mode. That's the typical associated with the superfluid case for the Hadamard bosons. And if you are in a weak interaction. All right. And what is the picture associated with the time crystal phase? It's very remarkable, especially at the half filling. And what we found at any given time along the spatial axis, you kind of like talking about half filling, right? You have like a particle number is like 0, 1, 0, 1, 0, 1 pattern. However, we have this time crystal. So it's like you have time lattice spacing. You have time lattice constant. At a second half of the time period, you realize 0, 1 become 1, 0. So it's very interesting. So it's like at one time, it's like 0, 1, 0, 1, 0, 1 along the X. And then in the next time, it's like 1, 0, 1, 0, 1, 0. So it's kind of like shifted. And you have this kind of symmetry breaking along one direction like that way. And you still have a remaining continuous translation invariance along this 45-degree direction. And I think Sasha has opened the window, which means I only have 5 minutes. Yes?
Yes.
Okay, I'm going to try to finish in 2 minutes. And it seems to me this is a new phase. It's not a multi-insulator, not a superfluid, because multi-insulator have full gap, but you do not have a algebraic decay in this Green's function. If it's full superfluid, it should not have a gap. So it's kind of like a very unusual, I would say, unconventional. We're still yet to discover more. Seems to be third phase in the well-known Bose-Hubbard model. So what about the temperature crystal idea? So if you plot MS, which is the charge density order in a time, in a spatial sense, as a function of temperature, then you realize, in particular, plot is function of the inverse temperature. You see a periodic oscillation with the period set by beta 0. And the beta 0 is roughly set by this minima right here, by this potential minima in time space. So you kind of have like a time lattice constant, which is given beta 0, which is associated with, you know, the minima of this potential right here. And it's periodic. And so I, of course, cheat a little bit. It's not really temperature crystal. It's actually should be inverse temperature crystal. In a sense, you actually is a periodic in the inverse temperature. But otherwise, we understand what that means. So that's actually what it means. And the imaginary time crystal is the microscopic mechanism. You have this long-range order symmetry breaking. In the thermodynamic level, it manifests as a temperature crystal. So that is actually an idea. All right. So I think with that, I just want to summarize. I talk about the two ideas. One, you can have a clean quantum model to show the Floquet/district time crystal without disorder, many-body localization. That's actually the idea, as the particle model shows. Second one, I propose a model and for the kind of like a temperature crystal. And with that, I want to thank you for your attention.
Thank you very much. We have time for questions. I think that Lin Zhenguo was the first. So.
Okay, thank you for this very nice talk. I I just have a comment. I think this non-Markovian interaction you are looking for maybe already exists. Maybe you can look for some papers about giant atom or non-Markovian giant atom. There they use the superconducting artificial atom to couple to surface the acoustic waves. And because the sound speeds are very slow, and there will be some kind of a loop, time delay loop, then the atom state is kind of determined by the past. The effect, although the original model is time, the original Hamiltonian is time independent, but the effective one maybe it's the non-Markovian interaction you're looking for.
Wonderful. We definitely, I should learn more from you. That sounds like very exciting. So,
so it's giant atom.
That will be, we should talk more. So that's really a physical system. I should definitely learn more. And it sounds like very, it seems to me very reasonable and very exciting to, like you said, it's the effective induced one is time dependent, non-Markovian, right? Yeah. So the key, do you have a minimum? That's actually.
I'm not sure. Let's maybe talk more.
If it's monotonic decay doesn't work, you need a minima, something like that. That's actually the key. You need like a minima going down and up again. Yeah. So we will talk more. Thank you.
Okay.
Yeah.
Thank you.
Yeah. Let's keep in touch in email. Yeah.
Thank you, Rosario.
Yes, I have a question about the imaginary time crystal. If you do analytic continuation of the response function, shouldn't you observe also a peak at finite frequency in real time?
Yes, they imaginary this oscillation in the imaginary will give you like decay, if I understand. If you're
right, but I mean, if I do analytic continuation and I go from imaginary Matsubara to real time Green's function, I think the same structure should give a structure at omega 0 of some kind. I don't know. Or at least this is my question.
If you have a decay in the imaginary axis and you do the weak rotation, you would get the oscillation in the real time. So I think the question is very profound. So the question is whether you can get something in the real dynamics. Yes. So I think it would be very interesting to see how this idea would be generalized while you're still not getting into the local theory and other things. And so I think it would be, I think the answer should be yes, if you think about the mathematical level, right? So that's actually my answer. Yeah.
Okay.
Yes. Okay.
Thank you very much, Vincent. I think we are going to the next speaker.
Thanks so much. My pleasure.
Thank you. I would like to introduce to you Al Shapere, who is going to talk about mechanical time crystals. So Al, the screen is yours.
Okay, sorry. Everybody hear me? Good. Okay.
Yes.
Good. Okay. Well, thank you, Krzysztof and all the other organizers. It's very exciting to be here at this this conference, and I only wish I could have attended more of the talks because of the time difference. I'm afraid I only been to the afternoon talks, but I'm hoping to catch up on the morning talks, the recorded versions of those. So anyway, but it's great to be a part of this conference. I want to start off since it's kind of amazing how far we've come with time crystals. We're approaching the 10th anniversary of the first two papers on the subject. And I think it's appropriate to take a quick look back at the origins of time crystals. So as far as I know, the first mention of time crystals is due to Doctor Who, of course. And in Doctor Who, it may already have been mentioned in some of the talks, but the time crystal plays a key role there in providing the power source for the TARDIS, which is able to travel in time, of course. That's Doctor Who's time machine. The term was used about the same time back in the 70s by biologist Arthur Winfrey to describe self-organizing oscillations and rhythms in biological systems. So for example, circadian rhythms or cardiac arrhythmias. And these are all non-equilibrium driven systems. And so one could say we've in some sense returned to that original paradigm with all of the talk about flow case systems and so forth. But time crystals as we know them were born in the summer of 2010. And I must say it's one of the more exciting moments in my physics life. I was visiting my former advisor and friend, good friend, Frank Wilczek. And Frank had been thinking about I'm sorry, what happened? There we go. About spontaneous synchronization of oscillators. And which is actually something that Arthur Winfrey also had thought about. And I came to visit Frank in Cambridge, and we took a long walk around Fresh Pond trying to sharpen questions and come up with physical examples. And we focused in on the question, which is a familiar question to us all now, which is at the time maybe was not so obvious to even pose this question, which was, can time translation symmetry be broken spontaneously? In other words, can the ground state of a system, either classical or quantum, be time dependent? Well, after a little bit of thought, we realized that it was not going to be an easy symmetry to break, that time translation symmetry is really a privileged type of symmetry that has some, that basically is built into Hamiltonian mechanics and a lot of the physics we're familiar with. So in fact, you can easily show that a system described by a reasonable Hamiltonian cannot have a time-dependent ground state. And Frank mentioned this in his colloquium, but it's such a simple argument, it'll just take me 30 seconds to recap it. So what we want, suppose we're given a Hamiltonian and we want to look at the ground state of that Hamiltonian. That means we want to minimize the energy. To do that, we minimize the gradient of the Hamiltonian. And if we combine that with Hamilton's equations, you can see instantly that this says that P dot and Q dot must be 0 whenever we're in a minimum energy solution. So that gives us a classical no-go theorem for time crystals because for a system governed by a Hamiltonian that for which we can apply Hamilton's equations, one always finds that the minimum energy solution is time independent. So that didn't stop us. We said, what about Lagrangians? And it turns out you can actually get somewhere with Lagrangians. So we tried a simple Lagrangian with its key feature is it has this wrong sign kinetic term here, or unconventional sign, let's call it. And kappa here is some coefficient, which I'm going to dial later on, but we'll take kappa to be positive. If that happens, we have something like a double well kinetic term with a negative mass, and it's analogous to a double well potential that one might find in more conventional systems, except that it's a double well in the kinetic energy, and or double well rather in the velocity. So classically, just as this would be true if this was a regular potential energy, there are two minimum energy solutions, and they spontaneously, each of them spontaneously breaks parity symmetry. Of course, quantum mechanically, it's true that the true minimum is a superposition of these two broken symmetry states. And so at least in this simple system, quantum mechanics undoes the symmetry breaking. All right, so to proceed, we construct the energy out of this Lagrangian. And the energy indeed has a double well form. It looks almost the same as the Lagrangian, except for this 3 here. And it's minimized in the velocity by non-zero, 2 possible non-zero values of the velocity, one right moving and one left moving. And so we have a whole continuum of solutions parameterized by the initial value x naught. So this is what we mean by a time crystal. And if you want your crystals to be periodic, then you can just take x to be an angle variable. Okay, so what about our theorem that you can't do this? Well, here's how we get around it. We'll be talking about loopholes later in the talk as well. So in this case, what's different from our assumptions in the theorem is that, first of all, momentum and velocity are not linearly related. They're non-linearly related. And that means for each value of the momentum, there are up to 3 possible values of the velocity. So if you convert our energy function on the previous page here into a Hamiltonian and write it as a function of p, it's going to be a multi-valued function of p. And you see for these values of p in this range, there are 3 possible values of the momentum and the energy, or sorry, of the velocity and consequently the energy. And so we can also instantly see what the loophole in the theorem is, which is this Hamiltonian is not differentiable at the minima. And that was our key assumption that we made in order to show that the ground state was time independent. So this is the type of Hamiltonian you want to be looking for if you want, at least classically, a ground state which is time dependent. And this turns out to be, it seems very strange from what we're used to from our paradigms, but it's quite robust. In fact, generally for Hamiltonians with higher order terms in the velocities, or rather for Lagrangians with higher order terms in the velocities, one obtains Hamiltonians with these features that one has cusps at the minima. So in fact, any non-convex kinetic energy is going to lead to this type of behavior. We call such systems mechanical time crystals, and they evade the no-go theorems because the Hamiltonian is pathological. Just to recap, it's singular with those cusps. It's also non-polynomial in the momentum, and it's multi-valued. So it shouldn't be surprising that these Hamiltonians have some unexpected properties. On the other hand, the Lagrangian is well behaved, and equations of motion, in fact, are solvable, and even with a potential, we can solve them. But we will find that the solutions have some peculiar properties. Let me just make a brief aside. I don't have much time to say this, but just regarding what happens when you have terms which Hamiltonians, or Lagrangians rather, which are higher order polynomials in the velocity. It turns out there's a very nice generalization and can be framed in terms of catastrophe theory. So for the Hamiltonian we've been talking about, at a particular value of kappa, if I plot the energy surfaces here, the Hamiltonian as a function of momentum, and also as a function of that parameter kappa, I sweep out exactly René Thom's swallowtail catastrophe surface. And it's a beautiful observation that if one takes higher order polynomials in the velocity, you in fact create the entire A series, principal series of catastrophes. So this gives a very nice classification of mechanical time crystals. All right, so let's make our first generalization, which is to add a potential energy term. All right, so we're going to add some v of x, and we're going to probe this potential near to the minimum, so we'll assume it's a quadratic potential. And if you do that, then here's our potential right here. Then, and you write the energy as we did before, then the the variable x is going to try to minimize the kinetic and potential energy simultaneously. But the problem is that these two conditions are incompatible because the kinetic energy tells us that the particle wants to be moving, while the potential energy tells us the particle wants to be sitting still at a minimum. So how do we resolve these, this tension here? Even for non-minimal energy solutions like this one here, there's a problem, or at least an unusual feature, which is that the equation of motion here, which looks like it has a kind of a effective mass term depending on the velocity, this equation of motion becomes problematic exactly at our critical value of the velocity. Because when you're at that velocity, this coefficient, this effective mass vanishes, and any force at all, that should be a v prime, by the way, any force at all is going to produce an infinite acceleration. So let's explore these solutions a little more closely. Suppose we're near the bottom of the potential well, and right at the bottom, as we've said, the velocity is going to want to be close to this critical value. And in fact, you can easily show that at the turning points of this motion, as it oscillates back and forth in the potential, the velocity will be exactly equal to the critical value. So you can, our first hypothesis was that what happens at the turning points is that the particle attains that critical velocity, and as we saw before, that allows for an infinite acceleration so that the particle suddenly reverses course and it doesn't slow down and stop, it just keeps moving at that velocity and suddenly turns around like it hit a brick wall and it moves the other way. So here's a plot versus time of this type of motion here. It's basically a triangle wave. And this is how we reconcile these two apparently contradictory conditions here, that we at least except at the turning points, we are able to satisfy that we're at the minimum or very close to the minimum of the potential, and we are moving at that critical velocity. If we're very close to the bottom here, then it turns out that the frequency of oscillation grows with energy, grows as your gap above the minimum energy decreases. So as you approach that minimum energy point, you approach an oscillator and oscillating with infinite frequency. And this is quite a singular situation. So I think to explore it further and to really understand what's happening at these turning points, a regularization is required. We'll find one by constructing a physical realization of this system. All right, the realization is going to be something like a Hall conductor setup here, a two-dimensional conductor in a perpendicular magnetic field with a tangential electric field. And we can describe it by Lagrangian like this. And let's see. Yes, so F is effectively the derivative of this function. F is the magnetic field, and G is giving us our electrostatic potential. Okay, and we're going to allow these fields to both be non-uniform. All right, so one finds these equations of motion, and in the mu goes to 0 limit, this first equation reduces to y dot as g prime over f prime. So the trick is we're going to choose f and g in a particular way, a very particular way, so that when we make the substitution y dot, when we eliminate x out of this equation, we'll get a Lagrangian for y that looks just like the time crystal Lagrangian that we've been talking about. So we're going to make this very specific choice. We'll take f to be this polynomial and g to be that polynomial. Again, these are non-uniform potentials for electric and magnetic fields. Then the ratio of their derivatives gives us simply y dot equals x. Okay, we needed this extreme fine tuning in order for this to work. And of course, you'll notice that this is well defined, except at the point where f prime is 0. That's the point of vanishing magnetic field. And but elsewhere in this limit, y dot equals x. That's the limit of mu goes to 0. So if I plug this into our Lagrangian and set mu to 0 and eliminate x using this equation here, I get back the time crystal, simple mechanical time crystal. Okay, and when I turn mu back on, it acts as a regulator. And that's going to, what it's going to do is it's going to keep us from having large velocities. It's going to disfavor large velocities, and it's going to make the behavior at turning points better behavior. At least it's going to tell us what's happening, allow us to blow up what's happening near the turning points. So with this regulator, it turns out the velocity does not simply reverse at the turning points. And follow this gold curve down here. Okay, the blue one is our x variable, and we're not going to worry about that anymore. But this is what the solutions look like. They climb for a while, they reach some point along the potential, they climb to the right here, and then they suddenly spring back, snap back to where they started. Okay, it's like Sisyphus pushing his rock up the mountain, and at the top it suddenly rolls back down to the bottom. So we call this Sisyphus dynamics. The motion appears quite jagged, but at finite values of mu, it's not. Everything smooths out. Here's I think the value of mu here is maybe 1,000th, and here it's 1/10, and you can see everything looks nice and smooth. An interesting point is that successive waveforms here, it's not simply periodic like a triangle wave. It's successive waveforms are not the same. They oscillate actually between two types of forms. And you can see it better if you enlarge the amplitude. Okay. And what's actually happening here in this solution is we're exploring these two branches of the Hamiltonian, of the as we move. I think the steeper curve is moving along the upper branch here, and the flatter curve, or the less steep curve, is the lower branch here. So we're oscillating between branches. You can find interesting dynamical phenomena as you vary parameters. For example, if you change the initial conditions, you can see phenomena like period doubling starting to happen. So here we had an initial condition. I don't think I wrote it down, but the initial velocity here was 1. So, oh no, I guess this is the same picture here. Okay, initial velocity is 1, and initial position is an arbitrary value of 0.7. And these are the conditions in x, not in y. But it doesn't matter. I'm just treating these as external parameters here. So or controllable parameters. As you vary these initial conditions, as you decrease this parameter, 0.7, you can see that the two parts of the period here become more and more distinct, and this wider part widens out even more, and it flattens out close to the x-axis. Okay, so here's 0.651, and now we go to 0.650, and you can see that this part of the trajectory here flips over suddenly and goes back to the left side of the potential, and then it comes back up, makes 2 trips back up to the right, and it goes back down on the right side before repeating. So between here and there, the period doubles. If you continue, not even by very much, decreasing this parameter, you can see that we retain this kind of 4-phase period here. All right. And just a word about why we get period doubling. Turns out that this point here, the transition between these two behaviors happens when the energy of the system passes through zero. And that's the point where we go from having two ranges of motion, one on the right and one on the left, to a single range where you go back and forth all the way from right to left. And that's the reason for the period doubling. All right, so that is one very useful regularization of time crystals. And I want to emphasize that this is not the only way to regularize. I want to show you another regularization. It'll turn out that this leads to very different macroscopic behavior. Even though we're just changing by a very small amount, we're going to add a small term proportional to the acceleration squared, to the Lagrangian here. Okay, and epsilon we're going to take to be quite small, of order 10 to the minus 5 or 6 in the pictures I'm going to show you. Kappa is again our other parameter, so we're gonna look at dependence on these parameters here, and we'll find a very different behavior. Now I should give you a word of caution. This is a singular perturbation. We're adding by adding terms involving higher derivatives than first order derivatives, we're introducing effectively new degrees of freedom and enlarging our phase space, increasing the dimensionality of the phase space. Okay, and this also, as often happens with singular perturbations, will introduce some instabilities. So, but let's proceed though. Let's take epsilon to be 1/1000th and solve the equation of motion here, which looks like what we had before, except for the epsilon term. And you get exactly what I told you we were originally expecting for time crystals, which is this triangle wave sort of pattern here. All right, with sudden reversals at the turning points. Well, it looks nice and neat, but if you look very closely here, you'll see what looks like maybe some numerical errors near the top here where the curve wiggles a little. But if you change the initial conditions, you'll see that those wiggles blow up and we get some rather, well, what we've done is uncovered some instabilities. And these instabilities are persistent and generic and even chaotic. So this was just changing the initial velocity from 2 down to 1 that we obtained this kind of picture here. And if I plot the velocity on top of here, this is the velocity as well as the position, you can see the velocity is going absolutely haywire. And if I continue varying that initial condition, I get even more complicated, bizarre, and chaotic type of behavior. So you've seen that these two different regularizations lead to very different outcomes, very different macroscopic behavior. Both of these regularizations involve singular perturbations and add new degrees of freedom. In the Sisyphus case, it was this X degree of freedom that we added. In the Sisyphus case, the motion we found is discontinuous in the limit that the regulator goes away, but stable and periodic. In the higher derivative case, we found discontinuous velocities at the turning points and severe instabilities and chaotic behavior. Which is the right regularization scheme will depend on the microscopic properties of the system. You might be wary of introducing the higher derivative regulator, but as I will explain, this is not an unreasonable thing to do. I see that my speaking time is up. I will just flash through a couple more slides here. This is a spatial version of the mechanical time crystals here. These are materials that have ridges in them that form spontaneously. And let's see, quantization I will not talk about. I'll just say that that it is possible, quite straightforward, in fact, to quantize the Sisyphus regulated time crystal, and you can calculate eigenfunctions and eigenvalues. And the interesting thing is the ground state wave function shows no sign of spontaneous symmetry breaking. In fact, it's just a symmetric superposition of left and right moving waves corresponding to two degenerate classical solutions. So, and we should not have expected in this case to find spontaneous symmetry breaking. Spontaneous symmetry breaking is a quantum field theoretic, not a quantum mechanical problem. And our field does not have enough degrees of freedom in order to see it. You need at least a 1 or 2 dimensional field. I will mention that we've looked for possible quantum systems where you could find this type of energy curve or dispersion relation. In fact, such systems are known. One-dimensional cold atoms are the simplest of those in modeled by Gross-Pitayevsky with a repulsive delta function potential, periodic delta function potential, has swallowtail shaped bands. And if you make the potential attractive, they point downwards, just like ours, although the ground state is not. So you could study this metastable band here and look for time crystalline behavior. And indeed, you find phenomena that might be interpretable in that way. These are soliton trained states found in this type of band here, like band 3 experimentally. And I'll leave it as a question for the cold atom people, whether these really deserve to be called time crystals. Last thing I'll say is that in cosmology, one encounters Lagrangians, which have very similar Lagrangians to what I've described. And in fact, they also include terms like acceleration squared terms. And so they may well be time crystals with a higher derivative regulator. And this, in fact, is the precise scenario for Starobinsky's original model of inflation. And so it's quite possible that the universe itself is a time crystal. All right. Last thing I'll say is, where do we expect time crystal Lagrangians to arise? Where do we expect higher derivative Lagrangians like this to arise is what the question really is, because as we've seen, this kind of behavior is generic when you have higher derivatives. Well, in effective field theories, we consider theories involving low dimension operators with coefficients that are fixed by experiment, and those in general will have higher derivative terms. And for large ranges of coefficients measured experimentally, we'll expect to get non-convex kinetic terms. What about the famous no-go theorems? Well, all of these will violate some of the hypotheses. For example, we'll have multi-valued Hamiltonians, which were not considered in the no-go papers. These Hamiltonians describe dynamics, at least classically, which are kind of singular, and the scaling properties are kind of unconventional as well. And and also if you look at metastable ground states, like I mentioned in the case of cold atoms or non-equilibrium situations, you also have a way around. So these are just effective theories. They're not complete fundamental theories, but they're an enormous class, and they're quite, as I've said, generic when you have higher order kinetic terms. So we should be inspired, I hope, to look for more systems that break continuous time translation symmetry in this way. And I encourage everybody out there to go out and find some more. Thanks. Sorry that I went over.
Thank you very much. We have time for 1 or maybe 2 short questions. Yes, Rosario.
Yes, you showed that you said that in the quantum version does not show any trace of time crystal. My question is about the semi-classical regime. So do you observe any trace of this behavior? I don't know, perhaps with for a limited time range?
Yeah, that's a great question. Well, in the semi-classical regime does allow tunneling, and tunneling is what causes these two broken symmetry states to superpose with each other, and that's what means that we lose the time crystalline behavior in the quantum case. But that's primarily, that's a quantum mechanical phenomenon. In quantum field theories, it can be much harder to tunnel between vacua, as we know from standard examples of spontaneous symmetry breaking. And so that's the, in semi-classical quantum field theory, I think you can, that's where you may expect to find this time-dependent ground state phenomenon.
Okay, last question, Thomas.
You seem to have these two timescales in the Sisyphus dynamic. So is two different timescales something I should be looking for in the experiment to find a system like that?
So you mean the two time scales of the
quick jumping and the slow return? Yes.
So the quick jumping is your regulator time scale. That's introduced by your epsilon or your mu, the small parameter you introduce to smooth things out at the turning points. And so that is going to be governed in general. That's sort of your cutoff scale for the extra degrees of freedom that when they come into play. Okay. But if I was an experimentalist, what I would look for is not just this funny jittering behavior near the ground state, but even at excited states, say involving solitons, semi-classical objects like solitons, where you'd be able to describe it effectively by a classical theory. I would look for this sudden change of velocity either, or sudden jumping. And I don't know if people have observed that in these soliton trains. My understanding is when they come to the end of the trap, they tend to break up, so it's hard to make measurements there. But that would be something I would.
Thank you.
Okay, thank you very much again, Al. So we have to move on, and the last speaker of the conference is Arkadiusz Kosior from Max Planck's Institute for Complex Systems. Arek, the screen is yours.
Okay, hello and welcome. So let me share my screen now. Okay, maybe I'll minimize this one. Okay, so hello and welcome again. My name is Arkadiusz Kosior, and I'm currently affiliated at the Max Planck Institute in Dresden, Germany. So today I would like to talk about condensed matter physics in temporal lattices, and in particular I will show you how to realize a specific quantum simulator of flat band many-band physics in inseparable temporal potentials with the Mobius strip topology. But first, let me thank my collaborators on this project, without whom this work would never come into being. And the most part of this talk, the main part of this talk, is based on the following paper, which we submitted to archives just a few days ago. So comments are very welcome. So I will start with the structure and motivation behind this talk. First of all, throughout this paper, I will consider so-called gravitational bouncer model, which was introduced in 2015 by Krzysztof Sacha, as a first manifestation of a discrete time crystal. So let me mention here that this is also a disorder-free model, like the one that was presented to us by Vincent Liu during the first part of his talk. And one of the greatest advantages of this model is that it allows for a drastic symmetry breaking, where symmetry broken states evolve with a periodicity up to 100 times longer than the periodicity of a drive. And as you remember, the big time crystals were the topic of Peter Hannaford's talk on Monday. In this introductory report, I will also show you how the discrete time translation symmetry can be broken in this model. Another important manifestation of this drastic symmetry breaking is that we can actually realize big crystalline structures in time. And as a specific example, I will show how to realize a system with properties of a two-dimensional time crystal, which lattice geometry can be designed with a great flexibility. And also, I will show that we can have exotic, tunable long-range interactions in the system. These two features together make a unique platform for quantum simulations in time crystals of condensed matter physics, both the known effects in condensed matter physics, but their temporal analogs, and also the effects that go beyond the standard condensed matter physics, which are also inaccessible by the standard quantum simulator platforms. And as a specific example, I will show how to realize a simulator of a flatbed body physics in the temporal lattices. At this point, let me also acknowledge that condensed matter physics can also be studied in phase space crystals, which was a topic of Lindsay and Guo talk on Monday. If you have not seen it, I refer to his excellent review paper on this topic. So let me begin with a one-dimensional gravitational bouncer model, where ultra-cold atoms are bouncing on a mirror in the presence of a gravitational field. Let me first assume a classical description and assume that the system is non-interacting for now. It turns out that in a classical case, without a drive, so where the mirror is static, all trajectories of classical particles are periodic in time. However, with a drive, when we turn on the mirror, let's say that the mirror oscillates at some frequency omega, only resonance trajectories are periodic. And this corresponds to a situation where a particle hit the mirror, which is temporarily at rest at its maximal or minimal position, so that there is no energy transfer. And in a classical case, we can have multiple resonances. A simple one-to-one resonance corresponds to a situation where we have a one mirror oscillation per particle hit. This corresponds to a period T solution. But also we can have higher resonances, like the simplest one, 2-to-1 resonance, where there are two mirror oscillations per particle hit. And this, of course, corresponds to a period T, 2T solution. However, in a quantum case, all Floquet states must obey the symmetries of the Hamiltonian. So all Floquet states must be T-periodic as the Hamiltonian function. However, it turns out that Floquet states corresponding to classical 2-to-1 resonance are shifted superpositions of two non-dispersive wave packets, which individually evolve with a period 2T, but this superposition is T-periodic, is T-periodic, as it should be, so that it respects the symmetries of the Hamiltonian. So after the one period of of evolution, the wave packet exchanged the positions so that the Floquet state has the periodicity of the Hamiltonian. Also, this is true for the interacting problem. However, for strongly attractive interactions, the particles prefer to group together in either one of the wave packets. So for large number of particles in the thermodynamic limit, the Floquet states is a superposition of two macroscopically different states, all of the Floquet states. So these are the Schrödinger cats, which are, of course, very, very prone to perturbations. I'm sorry. And even an infinitesimal perturbation breaks this Schrödinger cat, which collapses to one of the wave packets. And therefore, the symmetry, the time translational symmetry is spontaneously broken. And this is in a full analogy to the formation of space crystals. Let me also say that this mechanism for spontaneously symmetry breaking in this model is robust for imperfections of the drive, so that this time crystal is a phase and not just a fine-tuned point. For a stability diagram, I refer to the Veronica Gollett's poster, and if you have not seen it, you can check in their publication in New Journal of Physics. So as I have already mentioned, the high classical resonances allow for drastic time translation symmetry breaking. So we could have big time crystals where the symmetry is broken from 20 to 100 times. And actually, it turns out that big time crystals are more feasible experimentally in this model than a pure doubled time crystals. And this drastic symmetry breaking also allows us to create big crystalline structures in time, so that we could study condensed matter physics, temporal analogs of condensed matter physics. So in order to show how this crystalline structure emerges in time, I will quickly sketch the derivation of the effective Hamiltonian in the moving frame. Since a similar derivation was already presented to us yesterday by Hydros Labis, so therefore I will be brief so that we could have more time for questions. And so it turns out that the gravitational bounce, the theoretical description of this problem is easier when we switch from the laboratory frame to a frame where the mirror is static, but the gravitational field oscillates in time. This problem can be solved in a full quantum mechanical way. However, I will, for simplicity, and the illustrative purposes, I will stick to the classical description. And turns out that the unperturbed problem is fully integrable, and it can be solved using the action angle variables I and theta. The action I is a concept of motion, so that the unperturbed Hamiltonian can be expressed as a function of I only. And the angle theta is a t-periodic function, which is defined between 0 and 2 pi. Now, the full time-dependent Hamiltonian can be expressed in the same variables, and to do so, we need to decompose the Cartesian coordinate z as a Fourier series in the angles theta. And suppose now that we are at the general end-to-one resonance, which means that the frequency of the classical particle motion is a multiplicate of the frequency of the drive. And in the moving frame, which we go to by the linear transformation of the angle, all resonant trajectories are stationary. And therefore, if we are interested in the new resonant motion, the effective Hamiltonian in the moving frame should be time independent. And to show this effective Hamiltonian, let's do the two steps. The first step, we can neglect the highly oscillating phases in the time perturbation, which is basically the rotative wave approximation. And in the end, we have a simple single cosine, which is time dependent in the moving frame. Also, we can expand the unperturbed part of the Hamiltonian up to the second order. And in the result, we obtain the effective time-independent Hamiltonian in the moving frame, which has a form of a simple single part Hamiltonian in the presence of a lattice. And indeed, this crystal structure can be also seen in the exact first phase portrait of the problem as generated by the full time-dependent Hamiltonian. This first portrait shows the lattice structure of resonant islands. And if those resonance islands are large enough, then we can build on them in quantum mechanical Wannier states. These Wannier states in the lab frame corresponds to the wave packets evolving along resonant orbits, which break the time periodicity of the drive. However, for the non-interacting system, the particles will tunnel between different neighboring Wannier states, so that what we obtain is effectively the solid state behavior in the time domain. And now let me take a step further and consider a similar setup of two orthogonal oscillating mirrors. Since the mirrors are orthogonal, the problem is separable, and we can repeat the previous derivation almost exactly. However, we have now two independent degrees of freedom, so that the effective Hamiltonian is two-dimensional. So that in the end, we obtain a very simple system which has the properties of a two-dimensional time crystal. The two angles, theta x and theta y, as previously are periodic functions that are defined between 0 to pi, which, of course, defines the torus topology of a time lattice. And so let me represent the torus by a single square, where the opposite sides are associated with each other. In black, I've plotted a sample trajectory of a classical particle. So during the course of the time evolution, it meets the boundary and then respects the periodic boundary conditions and continues its motion. So in the result, the particle is wrapped around the torus. And now let's consider a very similar system, but now the two mirrors form a wedge of 45 degrees. Turns out that this system is also integrable, and this is because when a particle hits the mirror, it gets literally mirror reflected. Its trajectory is mirror reflected, so that we can do the local mapping to the previous problem. And when the particle hits the mirror, also the components of the Cartesian momenta are exchanged. However, now the system is spatially bounded, and it's twice as smaller as in the previous case. And is constrained in the Cartesian space, can be translated to the theta x, theta y space, and it induces this following condition. And this condition actually cuts out the parts of the space and introduces two new boundaries. One of them is a hard boundary, which corresponds to a pathological classical trajectory along the vertical mirror. And the other boundary corresponds to the collision with the mirror. And the topology of this space is probably better. It's better to see the topology if we shift one of the angles by pi. So when a paired classical path evolves, it eventually hits the mirror, and then due to the exchange of the Cartesian momenta, it gets to the other side, and then the same in this direction. Here, the angles represent the twisted boundary conditions, and so we actually have a system with the Mobius strip topology. You can see the details. You could have seen the details on the Arkadiusz Kroś poster, and if not, you can see our recent preprint. But now let's consider two oscillating mirrors. And if the two non-orthogonal mirrors oscillate, then we have really an inseparable problem. As I've mentioned, we have a great flexibility in designing lattice geometries in the time dimension. And actually, this flexibility is probably greater than the engineering of optical lattices, because we can have as many harmonic frequency as we want by choosing different shaking protocols of the mirrors. And one of the simplest non-trivial examples are the Honeycomb lattice, like on the left panel, and the Lip lattice. So the Lip lattice is a Brava lattice with a 3-point basis. And because of this 3-point basis, the energy spectrum forms 3 energy bands. One of them is flat. So the particle in the Lip lattice can tunnel between the sides in a one unit cell with amplitude J1, and between sides belonging to the neighboring unit cells with the amplitude J2. And if the amplitudes J1 and J2 are different, then we have the energy gap separation between the bands. And this band gap will be important to us in a moment. But first, why are we interested in the flat band? So first of all, flat band has an enormous degeneracy, and we can choose the eigenbasis of this band in a form of localized eigenstates, which we can call the Wannier states of the flat band. And these Wannier states are localized maximally on a few lattice sides, which makes actually this problem feasible experimentally, so that we can load in the experiment atoms into the eigenstates of the flat band, and we can restrict ourselves to this band only. However, if the system is non-interacting, then there is completely no dynamics in the flat band, because the group velocity vanishes identically. However, we can induce the dynamics back through the interactions. And as I will show you in a moment, these interactions could be quite unusual, so that we and can be tunable, so that we obtain a quantum simulator of exotic many-body phases. And as long as the interactions are smaller than the energy gaps, then we don't have any band mixes, so we can, with a good approximation, stay in the flat band. So let's now consider the many-body Floquet Hamiltonian. where the bosons are interacting through the zero range potential. Now, if we expand the field operator in the eigenbasis of the flat band, then the most general form of the Floquet Hamiltonian is the following, where we have all possible two-body processes with the amplitude uijkl, which is the integral of 4 Wannier states. In a normal case, in a space crystals, this integral u decays exponentially fast with the distance between the Wannier states. But here we have a different situation on a temporal lattice, because in the lab frame, this Wannier states of the flat band actually evolve periodically in the physical space. And it turns out that even distance wave packets can physically cross at some moment of time, which actually induces long-range interactions in the model. And in addition, these long-range interactions are tunable for the Feshbach resonance. Namely, let's consider the situation that we apply the magnetic field periodically at times when some specific wave packets overlap in the physical space. Then we can modulate the effective amplitude uijk, and therefore we can engineer some exotic microscopic processes in the temporal lattice. However, not every possible process can be realized, because actually, even if the wave packets cross in the physical space, the coefficients u can be identically 0. And this is due to the momentum conservation of the wave packets before and after the collision. And therefore, we cannot have density-induced tunneling in our model on the flat band. Which processes are allowed? So quite a few, actually. First of all, if the scattering takes place between the same Wannier states, then we have a familiar on-site interaction, which is trivial. But also we can have long-range density interactions with different amplitudes depending on the lattice sites indexed. And I think that most interestingly, we can have long-distance simultaneous planar tunnelings as plotted in this figure, which conserves the center of mass of the tunneling pair.
4 minutes, Eric.
Yes, that's the last slide. And thank you. Just let me note that I did not plot all of the possible processes, but only just a few for the illustrative purposes. And let me stress again that all of these processes, all of these amplitudes are tunable, so that we end up with a unique platform for quantum simulations in time crystals, which can realize exotic many-body phases. The possible future directions that we want to analyze in the future include the constrained many-body dynamics or exotic superfluids or supersolids, but the list could go on. And so in the conclusion, I've showed that the gravitational bouncer model allows for the realization of big time crystals and for the study of condensed matter physics in the time domain. Additionally, we have a great flexibility in designing temporal lattice geometries. We have tunable long-range interactions and exotic long-distance hoppings. The solid features make a versatile platform for quantum simulations of many-body physics, which can go beyond the flat band, as we can engineer some more complicated lattices in time. With this, I would like to thank you for your attention.
Thank you, Arek. So time for questions. Okay, Thomas.
It's applaud, it's not a question.
Ah, okay, thank you. Rosario.
Yeah, I just wanted to ask if it's possible to have a complex value for the hoppings.
Well, yes. In principle, it is also possible to have complex values of hoppings.
Okay, you can have some frustration induced in this lattice.
Yes.
Okay.
Like we have very good flexibility in designing the lattice geometries, as I showed this are just only examples. But actually, like this lattice geometry comes from the shaking protocol of the mirror. And as I said, we can have almost as many harmonic frequencies as we want. So we can engineer quite complicated potentials, but also the frustration can be studied in honeycomb lattice. So it's quite easy to get the honeycomb lattice. Yeah.
Okay. Do we have questions? Okay, if not, Arek, thank you very much.
Thank you.
And so that was the last talk of the conference. So Rosario, this is your turn.
So yeah, I just want to spend 1 minute just to thank many people. So first of all, I would like to thank all the people from the ICTS, the technical assistants, the section that helped us a lot, especially Walter. I mean, I think we got excellent assistants, and they were really devoted to solve all possible problems. Thanks a lot. I would also to thank all the secretarial support, Monica, Adriana, and especially Victoria, for helping us in all the email exchange and fixing all details of the conference. Last but not least, I would like to thank all the speakers and all participants for just giving us the opportunity to enjoy these 3 days. I personally learned a lot of things. I hope you also enjoyed. Typically, you say that, you know, at some point travel safe home, but we are all at home, and so my wish is that we will be able to travel safely in the future to Trieste or somewhere else where you want to go. And so this is what I wanted to say, Christoph.
Yeah, I would like to thank first of all, Rosario, you for the great idea of the conference. That is perfect. I hope that not only me, but most of the participants also enjoyed the conference. And I would like to also thank all secretaries and all technical staff. It was a great pleasure to collaborate with them. Many thanks. Thank you. Okay, that's it.
Okay, so all the best, and hope to see you soon. Bye.
See you. Bye.
So, bye, Christoph. At some point, we have a chat in the next days. So just to see.
Great. See you. Thank you.
Bye-bye.